organized by the Department of Mechanical Engineering entitled Hydrogen 360-degree Unlocking the Potential of Sustainable Power. It is my profound honor to extend a heartfelt welcome to the distinguished leadership of Army Institute of Technology, whose presence adds immense value to the today's inaugural ceremony. Major General K.K. Chakrabarti, Chief Signal Officer, Southern Command, and Chairman of AIT, a visionary leader and an inspiration to the entire AIT team. Major General Uday Shankar Sengupta, Director AIT, whose guidance continues to elevate the academic excellence of our institution. Colonel M.K. Prasad, Joint Director of AIT, Dr. B.P. Patil, Principal of AIT. All HODs, we are truly honored and privileged to have all of you with us today. We extend our sincere gratitude to all the registered participants from the various institutes across the country. Your enthusiasm and overwhelming response reflects your commitment to the continuous learning and your belief in the future of sustainable power technology. We are delighted to have you as a part of this academic journey. With immense pleasure, now I invite Dr. UV Ausarmol sir, HOD of Department of Mechanical Engineering, to deliver the welcome address for this Atal FDP. Welcome, sir.
Thank you, Dr. L.D. Jatha. Good evening, sir.
Good evening, gentlemen. Am I audible?
Yeah,
Yes,
sir.
sir. Yes.
Clear and loud.
Okay. Thank you so much.
Good evening, all. Respected Major General K.K. Chakrabarti, Chairman of Army Institute of Technology, Major General Uday Shankar Sengupta, Director AIT, Colonel M.K. Prasad, Joint Director AIT, Dr. B.P. Patil, Principal, all the HODs, resource persons, and faculty members present over here. On behalf of the Department of Mechanical Engineering, Army Institute of Technology, it is my great privilege to extend warm and hearty welcome to all the dignitaries, resource persons, and the faculty participants attending the AICT-sponsored Atal Online Faculty Development Program titled Hydrogen 360 Degrees, Unlocking the Potential of Sustainable Power. I extend my sincere appreciation to all the faculty members, researchers, and academicians from the institutes across the country who have registered for this FDP. The theme of FDP, that is hydrogen energy and its 360 degrees perspective, has been chosen with a great intention and relevance. Today, the world is moving rapidly towards clean, secure, and sustainable energy solutions. Hydrogen stands at the forefront as an alternate fuel, promising zero emissions, high efficiency, and the diverse applications. Therefore, this FTP is designed to provide a holistic view on hydrogen as alternate fuel. Through this faculty development program, we aim to strengthen the technical knowledge base of faculty members, to encourage collaborative research, inspire innovation in clean energy solutions, and promote academic and industry synergy in hydrogen technologies. I express my heartfelt gratitude to AICT Atal Academy for granting approval and support for conducting this particular FDP. I also take this opportunity to appreciate the dedicated efforts of the FDP coordinators from our department, Dr. J.D. Patil and Dr. L.D. Jathar, as well as the technical staff of the department who have worked tirelessly to plan and organize this 6 days program. Once again, I extend a warm welcome to all the participants and wish you insightful and engaging learning experience. Now, it is my honor to invite our Chairman, Major General K.K. Chakrabarti, to deliver the inaugural address. Sir, we are privileged to have you with us today. We request you to kindly guide us with your visionary words. Thank you.
Okay. Thank you. Thank you so much. Good evening, all dignitaries, Director AIT, the Joint Director, the Principal, the esteemed participants, and faculty members of AIT. Actually, it gives me immense pleasure as Chairman AIT that to inaugurate an event where AIT is hosting this AICTS sponsored Atal online faculty development program on hydrogen 360 degrees, unlocking the potential of sustainable power. At the outset, I'd like to congratulate the entire organization team for selecting such a timely and visionary theme. The world today stands at the crossroads of a major energy transformation, one that demands a shift from carbon-based fuels to clean, sustainable alternatives. Among all the emerging solutions, hydrogen energy has emerged as a game changer. As we all are aware, hydrogen possesses unique qualities. It's the most abundant element in the universe. It can be produced from renewable resources, and when used, it emits only water, leaving behind zero carbon footprint. It truly represents the bridge between today's fossil fuel driven world and tomorrow's carbon neutral future. India, under its ambitious national hydrogen mission, is striving to become a global leader in hydrogen production, technology, and applications. The government's vision of a hydrogen economy aims to make India energy independent by 2047, a step that will not only revolutionize our industrial and transportation sectors, but will also open new avenues for research, innovation, and entrepreneurship. In this context, the role of academia becomes critical. Faculty members and researchers like you are the catalysts who will inspire, educate, and drive innovation in this field. Programs like this FDP provide a valuable platform to understand hydrogen technologies in a 360-degree perspective, from production, storage, and distribution to safety, policy, and industrial applications. I urge all participants to make most of this opportunity, engage actively in the sessions, collaborate with peers, and take up ideas that can be implemented in your teaching, research, and institutional projects. I take this moment to appreciate the efforts of AICTE and the Atal Academy for continuously promoting quality faculty development programs that nurture innovation, sustainability, and skill advancement. I also extend my warm appreciation to the Department of Mechanical Engineering for the initiative and dedication in organizing this FDP. With a deep sense of pride, I formally inaugurate this week-long AICT-sponsored Atal FDP on Hydrogen 360-degree, unlocking the potential of sustainable power program. I am confident that the discussions and insights shared here will inspire new research directions and contribute meaningfully toward building a greener and more sustainable future for all. My best wishes to all the speakers, participants, and organizers for a fruitful and enriching week ahead. Thank you and Jai Hind.
Thank you, sir. That was indeed a powerful and thought-provoking address. Thank you, sir, for your leadership and motivating words. Thanks a lot, sir.
It's my pleasure, and I wish the team and the participants all the very best.
Okay, sir. Thanks a lot,
Thank
sir.
you, sir. Thank you, sir.
Thank you. Now, moving forward, it's my privilege to invite our first speaker, Dr. K.V. Srinivasan. Welcome, sir. Yes.
Yeah, thank you very much, sir.
Yes, sir. Dr. K.V. Srinivasan, sir, has been working in TIFR Mumbai about 26 years and currently the scientist in charge of the low temperature facility at TIFR. He completed his BE Mechanical, ME Cryogenics and PhD in Cryogenics Engineering. He is the course lecturer for the PhD students at TIFR, INO and MSc students of Mumbai University. He is serving the member of Doctoral Research Committee by Homi Bhabha National Institute, member of Research Board in Swami Ramanand Tirth Marathwada University Nanded, and the member of Academic Council of Sanjay Ghodawat University Kolhapur and Rajiv Gandhi College of Technology Mumbai. He contributes a technical advisor for the cryogenic facilities of the various ICER, IITs, NITs, central universities. He is the principal investigator on many funded projects in cryogenics development and hydrogen technologies. He is elected member of ICC and also successfully convened 5 national conference and workshop. He also conducted many training programs on cryogenic facilities and hydrogen technologies. I welcome you, sir, for this FDP.
Thank you very much.
Yeah, yes.
Can I now share my screen?
Yes, sir, it's over to you now.
Yeah,
Yeah.
please.
You can share now, sir.
Yeah. Is it now visible?
Now we can see your screen. Yes, it is
Yeah.
visible to all.
Thank you. Yes, thank you very much, our Institute of Technology, for giving us such a wonderful opportunity to speak about the hydrogen. In fact, I have added another word also, cryogenics, because it's something like, in fact, for example, if it is a cryogenics, there is no cryogenics without vacuum. So when you talk of hydrogen, and the kind of application and the usage what is being projected, it is not a very easy task without taking into consideration of cryogenics. It's something like, the step towards the green energy fuel for the future. So the hence I will be spending both these hydrogen as well as cryogenics in my lecture throughout the thing. So we would be wondering why this topic is so important about it. I tried various think about it. That one thing which comes to my mind, I find very convincing, and I hope that it will also be very convincing to you in the sense that the future is green and hydrogen is a fuel. Hence, the hydrogen is the only option to go about. And I'm sure that the end of the FTB with the various experts who are going to mention about various parts of this, all this hydrogen and the combo, we're going to specially focus, and we will definitely agree with me that the future is green and hydrogen is a fuel. And that's the kind of a bottom line which I wanted to give it as like a punchline to my lecture, which is going to applicable for the entire FPB program. Now, when you are talking about the various element on the clean fuel, why we chose with hydrogen? Why can't something else again? Of course, hydrogen is a very clean and high energy fuel, and it about 3 times more powerful than the traditional fuel like gasoline, petrol, or whatever it may be. Roughly about 3 times more powerful in terms of energy content to it. And obviously, when chairman was mentioning about that, when it burns, it emits no greenhouse gases like CO2 or the only water or the steam is the gas which goes out of the system, which obviously it's going to be a very clean greenhouse. No gases will be there. And not only that, beyond as a fuel, it has a virtual feedstock for many other energy carriers. For example, if you have a hydrogen with you, you can convert into electricity or into the different system, or the transition of the energy can happen very conveniently and in a very effective way with when you have a hydrogen with us in the thing. But there is a catch. What is that? Hydrogen is abundant in the universe. I mean, that's the first element came out after the Big Bang. And in fact, any star you found, about approximately the 75% of the mass would be the hydrogen, and it founds in every star, okay, in the universe. However, the catch is that in the Earth, hydrogen doesn't available freely. It not as a hydrogen. No, this always gets bonded with some other element, most commonly the moisture or the water as H2O or even the hydrocarbon, which are all things. So it is not in a pure form, it is always in a combined form. In order to use as a fuel, as we know that hydrogen has a very high rich in terms of energy content, we need to break the bond to separate hydrogen from either H2O or the HC of the hydrocarbon. And of course, if you want to break the bond, you always need some energy. You have to put some energy to get that hydrogen bond broken so that you can separate hydrogen out of it. It's exactly the main point which you will remember, and I would request you to get it to you so that this is going to be the start point of our future lecture. So it is not available in a generic form, it's always in a bonded version with some other element, and need to break it, for which we need to have energy. And more than that, to use the hydrogen in any of the fuel sector or the any kind of energy sector, it should be as high as possible. In fact, it should be more than 99. In fact, the methodology should give something like 99.7% to have a better use, or it becomes less effective, or in some cases may not be usable at all. So the breaking of the element, energy required to break it, and the methodology to get the high purity, this is what the challenge which the entire world is now focusing on it, to get it more and more affordable at a more and more affordable cost at a very higher and higher purity. So the whole objective is to get a quality of hydrogen is to be based on the various method, and to avoid having that, for easy understanding, the quality of hydrogen is always categorized on the source of hydrogen. So if you get the hydrogen from source A, source B, source B, is nothing but that version of various purity, you term it as a quality of it. So this the quality is based on the purity, and that quality comes out from the source of hydrogen in which you can able to produce it. As we know, the splitting of hydrogen need energy. If you get hydrogen from fossil fuel, like from the natural gas, which is the most easily available, it's very cheap to get the hydrogen from that, but it is very highly carbon intensive. So we call it as an gray hydrogen. Okay. So this hydrogen is very has a lot amount of impurity, nothing but that carbon, which you need cannot be used directly for many other application, unless you'll have to clean it, or you have to make some other process so that you get that hydrogen carbon reduced by kind of carbon capturing process. So you do some, make the hydrogen, gray hydrogen, pass through some kind of a procedure where the carbon get captured actually, but still it is not a high purity, so we call it like a blue hydrogen. So it is not only the hydrogen and the purity, but the process by which you get it, because there are many other process. Many speakers in future talks will be going spend time about that, but I wanted to give a hint so that you start the further lecture without any more information. You can straight away get into the topic. So that's impression that I wanted to have. So I have an advantage of being the first speaker, so I take the liberty in doing that, which would be an advantage for me. So now, if I want to have a high purity hydrogen, so you have to have only 5 kind of renewable energy sources, like whether it's a solar energy from the process by which get, or by the electrolysis where you get a very high purity, what you call the green hydrogen. So the topic is how I get the hydrogen in green form or the high purity form, so that your uh, the operation or the usage of the hydrogen is very, very easier. Now, just for the understanding, when it is say that hydrogen has a carbon contact, what it really makes it? For example, the green hydrogen, if you start from the natural gas, when you produce 1 kg of hydrogen, it comes along with 9 kg of CO2. The carbon intensity is quite high. So we process various process, we produce 9 kg for CO2 per 1 kg of hydrogen. So we call it as a gray hydrogen, which has a very high intent or very high content of carbon dioxide. Now we go for the blue hydrogen, where it has a carbon capture methodology is there, right? So most of this carbon dioxide gets absorbed or removed, but still it has some about 0.8 kg of CO2 per kg of hydrogen what you produce. And then, of course, green hydrogen is obviously, we call it, it's about 99 or better than 99.7. So this what the whole objective is that. You may also wonder, it is not life start doesn't stop with the gray, blue, or green, but it's also several other colors are there. I'm not going to spend time on that. So basically, the you get the quantity of purity in between blue or gray with and the methodology by which you produce it. For example, the methane pyrolysis, what you get is a turquoise hydrogen. When you have the coal gasification process by which you get then brown hydrogen. So these are all color in terms of seeing that how much is the carbon content and by which process you got that source of the hydrogen. So this is what we think. But the sum and substance is what is the cost involved in achieving higher purity. And without that, we know it is not going to be of much use to us. And the current technology, what we have to produce high purity hydrogen or the green hydrogen, what will term in further the green hydrogen, the cost per kg is still not comparable to the traditional fuel. So if you are making an energy source or the vehicle of hydrogen, and the cost is going to be very high and many folds higher than the petrol, obviously the people will not drift towards the green hydrogen unless it becomes the cost is comparable with that. So the current focus is to get the very high purity at an affordable, cheaper cost. Let's see in further slides to get the feel of what we mean by these cost and the purity of it. So considering this process and the challenges, India is also moving towards a net zero journey, as the chairman mentioned about the quantum green mission, that India has pledged to have a net zero emission by 2070, and then by 47 you have to remove considerably down to 47. Okay, so assume for a country where nearly we have about 70% of the electricity or the power comes from the fossil fuel, mostly coal, thermal power plant, or the oil gasification, the gas usage. So India renewable energy capacity in the last 10 years has grown up threefolds, like from 77.37 gigawatts to 226, about 220, 230 gigawatts in 2025, over a decade. So this is going to be further go up when we are going to have more and more automatic vehicle or the other process which you are shifting towards the thing, and it will have more energy. So that point is to reduce this uh, carbon content, and you can't stop the energy consumption. It will be keep going higher and higher. The challenge is to get, if we make green hydrogen much affordable, the current cost is something like about $4 per kg. The methodology or the process, the whole world is trying to bring below $2, which is equivalent to our petrol cost, about 100 rupees liter or so. But it's very challenging. So we will put some kind of an in between benchmark to compete globally. People have not come down to $2, but even if the current cost of 3.8, if you can cut down by 30% of that, still we come to that global market. So right now we are much below, or the challenge is to bring down to $2, but we are in between. At least you bring it 20% less, 30% less than the 3.8 per kg, then you are also in the race. So to make it happening, the whole technology in producing cost-effective, high-purity hydrogen is what the whole research point happening. That's the main challenge, or the main aspects that which we are doing the quantum national green mission. If you see this graph, which I took it from Niti Aayog dashboard, and 70% of the power comes from, about 68-70% comes from the coal, thermal power plant. So if you change over from this point itself, it's going to be a huge thing, because other things are very, very less, which are already the renewable gas, non-renewable gas from solar, or the biopower, wind, hydro, nuclear. So the challenge is, how do we reduce this, or the make an alternative for this 60%, 70% this thing. So what we thought is that we have to become energy independent, because more than 70% of the power, or the any power, we are importing from outside, like coal or the LPG or the CNG. We are all major importers in the world globally. So to reduce the energy independent by 2047, to make some more, so that we make it more and more affordable within our reducing the budget of import by substantially, going for more nuclear, or more towards the more solar. These are all the challenges, and hydrogen is an add-on which you can quickly take off, and we can make the market more challenging. So India makes to become energy independent by 2047 and net zero by 27, and green hydrogen is the central to this vision, because anything happen in this is going to replace immediately, change the whole graph in a very different. So typically we need to have something like 5 million metric ton of green hydrogen per year to change this scenario. So government is taking up much farther. How do we go about? So Adani Industries sorry, is going to produce 2.1 million metric ton per annum of green hydrogen, whereas Reliance already is having something, going to scale up that by 3 MMTPA by 2030. So by 2030, we would achieve the target of 5.2 million metric tons. So together these two players, it could surpass the government requirement, possibly even before 2032. So lot of challenges is there, and how do we go about it? Now, when we are looking various application of green hydrogen, what is the real application happening? Whether it is an actually happening, existing, or proposed, what is happening? In Germany, the hydrogen powered trains are already replacing with diesel. The entire Tokyo Olympic Village was using green energy. Airbus is planning to have a zero emission aircraft using hydrogen. British startup has already come up with prototype of flight with hydrogen. Many of these combustion engines are switching towards hydrogen. That was also one of the topic we are going to see in the further slides. And large carriers are being towards shifted to hydrogen. And to start with, India is taking the first option of going for LNG, so that it is reasonably better in terms of green hydrocarbon content compared to the fossil fuel. So hydrogen, LPG to the final value. So hydrogen powered car, which are already in the market. So in Indian perspective, we have a pilot hydrogen buses are already running in thing, and we have a very large ambition project of hydrogen powered trains, which are ready to launch, successfully tested at ICF Chennai, and very going to soon. It's going to be a very large powered, and nobody else than for 12,000 HP powered track, which is different technology. We'll see that. So this breakthrough has proven that green hydrogen is no longer just a vision. It's actually going to transition, driving force towards the transition of our net zero future, not only for us, for the entire globe. That to have this happen, we need to have this thing. So with this background, I would like to shift the focus towards the, in terms of energy, how that carbon fuels, free fuels of like liquid hydrogen or the hydrogen based thing, how it can be used, and how do you use the renewable energy as storage in using cryogenics. And of course, I'm going to touch upon the LNG because that's a start point of the whole shift towards the liquid hydrogen or the green hydrogen. So these are the some of the things we are going to see in things. So before I move to cryogenics, I would like to bring it to our platform of the temperature and other things. So for example, you know that temperature can be measured in degrees Celsius or maybe degree Fahrenheit. Of course, you also have a degree Rankine. But we in cryogenics, we always use a Kelvin scale, which is nothing but an absolute version of Celsius. So whatever the, if you have a, what is a Kelvin scale, is whatever the degree Celsius you add upon 273.15, we call it as a degree Celsius. For example, the 22 degrees Celsius, we call it a 300 K, which is a typical room temperature of it. And the conversion can happen from various units from Kelvin to Celsius to Rankine or Fahrenheit. This is a conversion factor is there. So in terms of cryogenics, we always use Kelvin scale for measurement. And cryogenics is something like it's deal with the production and effects of very low temperature. It's a very special subject. It's also a comes under a physics and engineering, both in case of hand in hand with that. To make it more emphasis about the cryogenics and the temperature scale, I would like to show so what is the temperature in terms of higher temperature. We know that at 100 degrees Celsius, water boils, and then 0 degrees Celsius, water freezes, and typical normal body temperature is 37 degrees Celsius. Now we will try to see the higher value of the temperature. For example, that the iron ore melts around about 1500 degrees Celsius, and we know that sun surface temperature is roughly about 6000 K. It's a surface temperature, whereas the periphery of the sun would be some million degrees Celsius. Obviously, it's due to some magnetic flux happening at the surface of the sun, which produces very high temperature. So the surface temperature, the boundary temperature is much, much higher than the surface of the temp. And not only that, there are certain stars which temperatures are in more than 40,000 degrees Celsius. In fact, beyond certain value, we always measure the temperature in terms of color rather than the measurement theory. So typically you say that if you see from 0 degrees Celsius where the water freezes, on the higher side, it almost see infinity. There are certain stars with the temperature of 10 to the power 9 degrees Celsius. So typically it's like an infinite scale in the higher end. Now let us see what is the temperature below 0 degrees Celsius. And when you start from 0 degrees Celsius freezing point of water, and when we reduce the temperature, it goes to 273.15 and it ceases. There is nothing below that. So one side we are seeing 0 to infinite on the higher end, and the other end we are getting 0 to 273. It's something very, very insignificant compared to the temperature of 0 and the higher end. So a lot of property changes below that very insignificant band of 273 K compared to infinite K. So we are interested in this insignificant band of temperature, what you call as a cryogenic. And the cryogenic is the absolute zero, what you call it as an temperature, nothing below that. It's and you can't, it's nothing below that, and this only a theoretical limit. In fact, you cannot go practically achieve this temperature of minus 273. In fact, it's very, very precisely found, but you can't go below that. So we may wonder that, but something has been very precisely found, why it is not reachable. The sense that we slightly go into the physics to understand what is happening. We know that various gas laws are there. We must have studied in thermodynamics, Boyle's law, Charles' law, Avogadro's law. So let us see the Charles' law, which says that V by T is constant. As the temperature reduces, the volume of the gas reduces. So when the temperature keeps reducing, that volume keeps reducing, I think, which is nothing but Charles' law. What we do is we just simply extrapolate that Charles' law And we see that where it is getting at the temperature scale, it scales about minus 273.15. In fact, many digits have been precisely found. And this is what you call as an absolute zero. So, which we know that this is an absolute zero. The reason for why this is a theoretical limit and cannot be practically achievable in the sense that when we are reducing the temperature, we are having some gas and we are reducing the temperature of the gas, it become more and more dense, the temperature keep on reducing, and as we go very, very low temperature, then we go to a quantum level, which is not a multi-element, it's a few atoms. So few atoms are cooled lower and lower, and at this temperature, assume you need a one atom. Even if a one atom is cooled below certain level, at this temperature, we are seeing that molar volume is become zero. So the volume of the gas becomes zero at this temperature, but we are cooling the gas or cooling an atom. So the molar volume of an atom has to be considered for your calculation. It cannot be ignored. So it's a very, very simple reason or very provable reason saying that since the molar volume has to be taken into account, that absolute zero is the theoretical limit cannot be possible to go. So people have tried to go as close as possible to the power of 10 to the power of minus 12 Kelvin has been done, but of course that is with few atoms of particular material, so not below that. So this is a theoretical limit, we cannot go beyond this thing. Now we know that it is the basic background of cryogenics. How do we achieve the cryogenic temperature? So it's a simple cycle that we have a compressor. The gas at the inlet get compressed to the two, and the gas is passed through the heat exchanger and passed through the Joule-Thomson wall, which is nothing but that isenthalpic wall or the kind of an free expansion wall we all studied about in the thermodynamics. So Joule-Thomson wall is nothing but the isenthalpy remains constant at the inlet and outlet. When the high pressure gas is passed through the Joule-Thomson expansion wall, it produces low temperature. If the gas enough and gets liquefied, whereas the cold low pressure gas moves up into the heat exchanger, cooling the high pressure hot gas in the cycle and goes back to the suction where it gets mixed with the gas to compensate the constant mass flow of whatever quantity we have liquefied, so that the cycle works in a constant mass flow, so by which we can liquefy many gases. Of course, that practical application does not use this technique. So this simple technique is called the Joule-Thomson expansion cooling, what you call as a Linde cycle in terms of cryogenics. So we go to the next cycle, what is nothing but the Claude cycle, which is nothing but the modification of Linde cycle, where we have seen the Joule-Thomson expansion to increase the efficiency, because the Joule-Thomson expansion is an irreversible process. We know in thermodynamics, when you want to study the irreversible flow, will have a very less efficiency. When you are talking in terms of operational plant, we have to take consideration about the energy consumption or the energy efficiency in the cycle. So to have it, we add an expansion process, what you call isentropic expansion process. The high pressure gas is expanded in an expander, and the low pressure, low temperature gas is put back and then cooling the incoming heat exchanger. So we put some multiple heat exchanger. The gas which comes here gets cooled by the expansion power, and then which is further cooled by the evaporation gas, and then finally liquefied. So adding this expansion, maybe the number of expansion may be more, 1, 2, 3, depend, adding more and more heat exchanger, so that you reduce the temperature as much as possible in the way, and the final Joule-Thomson expansion produce cooling. So by which way all the gas can be liquefied, and in fact all the commercial cryogenic plants work in these kinds of expansion combination of a isentropic expansion and isenthalpic expansion in for producing low temperature. Okay, so having known this temperature, let us jump into this our subject of liquid hydrogen, which we are going to see, and liquid air and the liquefied natural gas. So liquid nitrogen is a cryogenic fluid because at atmospheric temperature, atmospheric pressure, its boiling point is minus 252 degrees Celsius, typically about 20 Kelvin in terms of Kelvin scale. And if you see the density, it's only 70 grams per liter. So very, very light fluid at that thing. So if 1 liter of liquid hydrogen is expanded, or if it's allowed to evaporate in atmospheric pressure, equivalent to 848 liters of gas. So you see that kind of a quantum of density is increases when you reduce the temperature. So 1 liter of gas, a liquid, will expand to 848 liter of hydrogen gas. Same with an air which liquefies at minus 194 degrees Celsius, about 79 K. And this has a density of 870 grams per liter, roughly about water, which is 1000 grams per liter. It's almost close to water at much dense fluid. And again, 1 liter of liquid air, when it evaporates, we get about 760 liters of hydrogen gas. So I put it in another where if you have an 1 liter vessel and we put some liquid air or liquid, whatever the hydrogen or whatever thing, when you close it and when you heat it from outside, the pressure build up, since it is not going out, the pressure build up will going to be 760 times. So 1 liter of liquid air at atmospheric pressure, when you evaporate by adding heat when the vessel is closed, the pressure of this vessel will go to 760 times the atmospheric pressure. So we said all the cryogenic system like a potential bomb, it's much worse than bomb. A same way that LNG gas, it's about minus 160 degree is close to cryogenic fluid of 114. Comparatively, this is much colder, slightly colder, and this slightly warmer in the sense compared to these two. And the density is about of a kg per liter. Of course, that depend upon the composition of whether the propane and butane mixture. And 1 kg of liquid nitrogen when it expand about 600. So roughly all these gases when it expand some 600 to 800 liters of gas of each liter. So this information is necessary to carry on forward so that we can safely handle. So whenever we talk of cryogens or very low temperature, they seem to be have a safety concern to it. It's very cold. In fact, it's much worse than the hot oil. It can freeze your flesh, freeze your skin, and prolonged contact with the liquid, any of these cryogenic fluid will become a painful blister because going to the low flow temperature fluid comes in contact with your body, locally numbs your sense nerves, and slowly it becomes, when it becomes warm after some time, it given very blisters. And of course, when nitrogen or oxygen or hydrogen anything expands, it condenses all the oxygen in the ground, and then you feel a situation that you cannot breathe because all the oxygen in the atmosphere get condensed with that very low temperature fluid whenever it is spilled out. So you have to careful that how do you quickly get that area clean and with the fresh air, this thing. Of course, you have to use when you are handling a lot of safety personal protective equipment to save you and the person who are working in a very way. So that's the background of cryogenics and then cryogenic safety part. Now coming back to our core subject of the hydrogen as a fuel. Now we go in detail that when you say that 3 times much powerful, if you see that hydrogen has an energy content of 44 megajoule per kilogram of petrol, whereas hydrogen has 120 megajoule. Okay, so it is a very high energy content. This can be used as a fuel for many applications, which we are going to see. The normal internal combustion engine can be converted into hydrogen combustion engine, or use that hydrogen to have the fuel cell, and the fuel cell packed engine by which you can produce. Of course, the rocket is another special application. We stick to these things. And of course, we know that there's no harmful emission when you use the hydrogen. But the main problem is storage of hydrogen is very difficult because it's very low density hydrogen. It cannot be stored as quick as a traditional fossil fuel. So what you call as a specific mass is a mass what you can store in a given volume. For example, if it is an hydrogen, you can have 15%, maybe it may be more than 80% if it is in petrol. So in a given volume, storing as much as liquid fuel is very poor in terms of hydrogen. So we have to take care of this problem either by condensing the liquid, like condensing the hydrogen gas as a liquid hydrogen so that it becomes more dense, so the specific mass can go up a bit, or you store it as a very high pressure. And we'll see in further slide that pressure is extremely high so that you can able to push store as much as mass in a given volume. So when you go for very higher pressure, the challenging of pressurizing and pressurizing of safety in terms of vessel handling, everything comes in that. So you also have a third possibility. We cannot, if the pressure compressing of gas is so high, it's very difficult, and liquid hydrogen as okay, but it's not much as a specific mass. To combine these two, give it in liquid hydrogen form and store it in a very high pressure, not as high as compressed gas. So the combination of high pressure cryogenic fluid is also one of the options, that how do we store the hydrogen, because that's very, very essential and kind of a storage. Over the production, how do we extract hydrogen? As you say, the simplest thing is the natural gas, which is much cheaper and quickly we can get, because the CNG gas, the wherever we get, we is quite, along with that we can have the gray hydrogen is possible, but is very cheaper, but it's not as pure for certain things. And we also have hydrogen production from biomass separation, which is a very promising area, that it can have a very high purity hydrogen is possible, but still it is not a very high purity like green hydrogen is somewhere between the blue and turkish blue waste. Okay, so that many of these challenges happening, how do we increase the purity in the waste biomass, because many of the city environment, the biomass collected can be quickly become a plant for producing hydrogen, rather than if it is an CNG, you will have to be imported, or it's in the oil rig, so it's far off. So if the hydrogen production comes within every city wise, the biomass is a quick option. And there are various other methodology like ammonia, that can have the high percent of hydrogen is there, again challenging in separating. In fact, the cellulose based section can also be used for producing thing hydrogen, and the various from the methane of various methodologies are there. Maybe speakers future, I mean the further speaker will give up. So but the common substance is that if you are producing from the traditional way, it's much cheaper but very impure. We are putting the electrolysis which is very high pure, and this is what the range we are looking at, but the cost is very high, something like 3 times higher. So we'll have to come somewhere below this or at this level. This was the whole challenge. So the cost is very high, and we are trying to reduce that electrolysis cost by 2050 is somewhat comparable with this gas reforming process. So the curve has to meet or go below that, and how quick before 2050 is what the whole world is running around. When I was mentioning that the biomass is one of the option, of course, it doesn't give the high purity hydrogen. The ISC Bangalore, along with an Indian Oil Corporation, come up with some kind of a membrane separation gasification plant, can produce highly oxygen, hydrogen rich gas. So instead of biomass to the traditional production of blue hydrogen, do some hydrogen rich synthetic gas and then separate the hydrogen from the synthetic gas, like a two-stage separation process by which we can produce the high purity hydrogen. So the technology to produce high purity hydrogen is already been seen. It's from 2000. The prototype models are being now in the process. So it increases biomass to somewhat blue hydrogen, then we make a synthetic hydrogen rich synthetic gas. From the hydrogen is separated, pure hydrogen is separated from the synthetic gas, is what the technique is, of course. The other very promising area which has been so fast going to happen much faster is about the internal combustion engine. We have an already all the fuel powered engines are available, normal internal combustion engine using gasoline powered, all the diesel powers are there. So if I replace the fuel from gasoline to hydrogen, can I use that is like an internal combustion engine? Yes, it is possible. Of course, there is slight modification has to happen, but we will see in the next slide that what is kind of an changes can be done. Is there any possibility without any change, just change it the in the carburetor supply of the petrol to the supply of hydrogen, whether can produce things? Yes, it is possible. Hydrogen engine burns internal combustion nearly identical as a spark plug ignition based with a slight modification, and it produces and has. Let us see. It's a typical IC engine where he has a gasoline comes with an spark plug. Everything remains the same, and you change the fuel plug from the hydrogen gasoline supply to the hydrogen, whether in terms of hydrogen high pressure gaseous spray of it. So hydrogen plus oxygen which comes from the carburetor air, which is a traditional way which produce high power combustion power can be utilized to drive the piston, and whatever you get, the exhaust is high. So H2 plus O2 is an emission, is a very green emission. If you have that kind of a system available, we can carry a liquid hydrogen or the high pressure gas hydrogen or the combined hydrogen gas, which we can take it with us and combine, evaporate it, and connect it to all this fuel line, like a fuel multi-point fuel ignition. Everything remains the same, just change from the petrol tank to the hydrogen tank, things are done. How this is possible? It's a simple diagram. Okay. So basically, when you are using the gasoline vapor, we know that the opening of inlet exhaust valve is based on the valve timing diagram of a thing. People who the automobile engineering will know about it, that valve timing diagram at valve sequence of the valve, which valve to open, whether the inlet open, exhaust open, both closed. So this valve timing diagram is there. So assume for a typical petrol powered engine of 1000 cc power, 1000 cc engine, roughly about 1000 cc engine, 983 total cc. So if we put about 1/10 of the fuel and remaining thing is about 10% is the fuel and 90% is the air, and get combust, and we'll get about 3.5 kilojoule of power, combustion power, which will drive the vehicle. Assume that the 3.5, we for a moment we take it as 100%. Okay, so a 1000 cc engine of petrol can be connected to gaseous hydrogen engine. Of course, instead of the content is very high, then we need to have, since the gases, the density has to match, so we need to supply more hydrogen, typically something like 30% hydrogen, and then about 60% of air, by which if you don't change any of this valve, piston, or the bore of the cylinder, just change the flow rate of hydrogen as 30%, reduce the air by 30%, so 60 combination. If we run it with the normal, the existing spark plug, we get something close to 3 kilojoule. About 85% of the power can be done possible without doing any change in this existing petrol engine, just by altering the valve timing diagram. So we reach about 85% of it. So without much change. So assume that if the hydrogen is there, this is what people would like to do, change into hydrogen powered vehicle, do it. So this is the best option. Now, what is the next option? That I can increase the bore diameter a bit, about 10%, 15% more, and then I can add this fuel intent also more, by which I can have a bigger cylinder, bigger bore, more fuel, little reasonably less air, by which I can produce 115%, 15% more than the existing engine without much problem. Of course, there are some design changes required, both in terms of valve timing as well as the bore and size. So any changes future can happen with this kind of a thing. Instead of this, we can want to still increase the power with the same diameter, same size. We can increase the pressure at which the fuel comes into the contact, so that the in normal condition the pressure comes in the normal atmospheric pressure, or maybe dripping. Now here it's going to high pressure, so the cylinder wall thickness, the pressure, sealant, leakage, everything has to be taken care, so that by which we can increase the power of the engine. So this is what is happening, but this has been, people are quickly changing. So if we have the know the diagram, by changing the valve timing diagram, we change all that existing power vehicle. We are doing this, what this Godrej and then Tata people are doing on that. This is how the people have done in other ways also. Okay, so this is the one very, very promising area which we can quickly take off the moment we get a high purity hydrogen. So all changes, you have to ensure that you need a high purity hydrogen. So the problem of getting hydrogen is what the main hurdle than the solution. Solutions are already possible, reasonably better solutions are available, but stuck with high purity at affordable cost. Okay, that you should remember. Now we go back to the next type of wheel, fuel cell based vehicle, which is also we can quickly change over from here. So India in principle have decided from 2030 not to produce any petrol or diesel powered engine, because I don't have a reference, but what I heard and what I understood, please cross check, don't take it certain. So this that from 2030 there no more petrol and diesel engine going to be produced. So we should go for either electric based vehicle, which is already in the market. You just go in a full swing. Now at the same time we are existing the hydrogen fuel cell is also coming up. If it is hydrogen is become more affordable, what do we do with the electric vehicles? So this combination of this electric and hydrogen is what the hybrid. This is going to be the future very soon. So how the hydrogen fuel cell works, which all these many experts are going to say in further talk. I just give some combination. When you have an two fuel sensors similar to batteries, you have a cathode and anode, and one side you pass through fuel, which is nothing but our in that case our hydrogen. Other side we push air, in fact, or the oxygen content of the air which we are in. So hydrogen is at one end and oxygen is other end. In between is separated by a membrane which we call as the electrolyte, which is very specific. And when this gas pass through this thing through the membrane, there's an energy created. We go back to the other thing. The H2O, when you want to separate hydrogen molecule from the electrolysis process, you put some energy to take it out. Now hydrogen and oxygen is combined here, will produce the energy back, which is what we are taking as an electric. So the breaking of bond, we need energy. Here the combination of bond will produce energy. That is what we are capturing. So this, because along this cathode and anode, we get some electrical current, which we take it and store it in a battery by which you can have. So obviously the hydrogen which comes here will also pass through some of the things producing some in the electron voltage here and comes here, it gets combined with an oxygen molecule and we get that H2O which is thrown out as an exhaust. So hydrogen goes through the membrane, pass through this energy barrier, membrane barrier, mix with oxygen and as a water it goes out. So typically if you see, yeah, each fuel cell as of now we do get about zero 0.8 voltage. So the zero 0.8 voltage is not um, enough to drive a vehicle. We need about 12 voltage or plus, then only you can drive it. So if you see that hydrogen fuel cells are 2 times efficient than internal combustion engine in terms of the fuel you put and the energy you get it out. So internal combustion engine is a 25%, whereas we get about 50% more in this one. Okay. Now, as we don't, this fuel cell based vehicle cannot have enough voltage. So the challenge is to have the proper voltage to run a vehicle. You add a stack of fuel cells, and there's a centralized path of fuel goes in here, will go to all the cells, and the air comes in from the other chamber, will go to all the thing, and each cell will produce an back electrical current. You combinedly take it out, which will get. So roughly about 45 to 47 fuel cells are stacked together to produce an voltage of about 12 plus to drive a vehicle. So that typically any drive vehicle, if you're giving zero 0.8 volt, you need to have a stack of such much voltage to run a vehicle, and you need the centralized fuel inlet and exit is what. Okay. So now about the membrane, of course, I'm not going to say much about it. There's many people in this line fuel cell people are going to mention about that. The different types of membranes are available, alkaline based or the proton exchange membrane, which is not like a polymer with this. So these technologies are much more higher by which you can change the everything remains the same. The what you get the best output, whether is heaven after some point of time the membrane has to be changed, or how quickly you can produce this electron voltage comes out from that, or how long it can stay intact. So these are the challenges. There are many types of fuel cells are available. uh, I just show for the sake, I'm not going to spend time on that. If you see all the thing stuck with that, what is the typical storage technology what you use? The conventional is in whether you can store it as a liquid or you can have a compressed gas helium. Then it's not only there. If this become very low temperature, it's not possible. If it is a very high pressure, it's not possible. Then you also have a steady state material where the hydrogen, like a sponge, when you hydrogen comes in, all the hydrogen gets absorbed in the sponge and it can release as and when required. So the storage technology can be a of many mold. It's not only a traditional liquid or gas, it can also be a solid state material, various materials at low temperature. This can happen as a room temperature, at a very elevated condition, or the higher temperature it can happen as a low temperature. So all combination exists possibly. Speakers will mention about that. Okay, so why I'm showing this slide is that we have all these electric vehicle in the market, and the fuel cell market comes into the thing. So you just have an auxiliary device, the battery will be there to start the engine. Once it starts, you get the power from this fuel cell coming from the storage, and fuel cell will produce the electrical current to drive the motor. Whatever the extra, it will store in the battery, and next time when you start it and then run. So it's like a combination of hybrid vehicle, like here fuel tank and the battery. So it can run from the batteries to start with, then it can take over from here, it can produce more or the equivalent. If it is more, it just give it and then store it in the battery and the normal transit. So these kind of an hybrid, whether it can be parallel or the series mode hybrid vehicles are being going to that. So whenever there is a fuel cell, the hydrogen problem is sorted out. All the hydrogen electric vehicle, by adding this portion fuel cell based one, it can go into directly an hybrid vehicle. This is what going to happen in future. So in a typical fuel cell vehicle, you need to have an electrical propulsion, which is a known thing. You need to have a fuel cell technology here and the hydrogen storage here. As of now, if you are looking at the hydrogen fuel cell based vehicle, of course the batteries are still there, so the battery can be charged externally or from here, so conversion becomes easier. And I was mentioning about the challenges in hydrogen storage. I was not saying high pressure. So when you are looking at the high compressed hydrogen gas of the hydrogen, you should compressed from 35 mega to 70 megapascal, sometimes 350 to 700 atmospheric pressure. Huge pressure, unimaginably high at room temperature. So if you want to make such a high pressure, yeah, typically you must have seen the gas cylinder in our LPG cylinder, it's about 3.5 atmospheric pressure. If you go the gaseous cylinder in the laboratory, you may get about 150 to 200 bar. But if 350 to 700 bar is the temperature at room temperature, very high. Of course, if you want to go as a liquid hydrogen thing, you can go into about 10 bar is possible. Then you can have a hybrid solution of high pressure and low temperature and high pressure combination will be take care of these things. So both the things are available in the tank pressure. So we are already making, there are market available in the market of composite fiber based wrapped cylinders. It's not a typical metal cylinder. The metal wire mesh over the carbon fiber, many such layers, such thing. We find make the thing. Compressed hydrogen goes up to 340 to 700 millibar. For example, if you have a typically about 186 liter volume, water volume of this capacity, and store it with about 700 bar of hydrogen gas at room atmospheric ambient temperature, we can have about 500-kilometer range with a fuel cell based vehicle. So the storage is not the 500-kilometer range, is that how safe we can do it, how quickly. When you have the storage, how do you test it, how do you ensure it is leak tight, because it's going to be sit in a vehicle which is very safety concern for the people who are traveling with that. Anything is to happen, so how do we take care of this? So this has to be that. Now if we want to have a liquid cryogenic based tank, we don't need to have a pressure, because we can slightly go little higher pressure, still affordable, but we can still match this requirement with an cryogenic fluid. So maintaining liquid hydrogen becomes very explosive when it comes in contact with oxygen or this kind. And so when you have the liquid hydrogen tank, before filling, you have to be extremely cautious to clean the cylinder, purge the cylinder with so many gases before it refilling. All the pipeline which is connected, it should not be exposed. So these are the challenges which we need to do. Of course, these are all been well proven. These are all been already done. Like for example, when you have a tank which is have a multi-layer insulated tank with so many layers of radiation layer to avoid the reduce the boil off of the hydrogen at the high pressure. Then liquid helium is pulled pour here, and you take the hydrogen or the liquid hydrogen or the hydrogen gas, depend upon the technology using here. And how do you make the cylinder, how do you fix it in such a way that the wall manifolds are accessible and filling holes are at the front. And when you make the filling holes, it should be the valve and other connections should be standardized so that the location where you are going to refill will have the matching adapter to that to get generate, which is already been done. Like you have a pump, petrol pump like that, with a liquid hydrogen pump, pushes thing through the vessel and dispenser and get stored into the system. In case some of the gas are using only compressed gas, you take the gas, compress the liquid, evaporate, compress, and put it back here. So whether it's a liquid, all the things are possible. I have a small video about this vehicle, which are showing about the electric motor. Okay, so this more about the that thing. So the next one is what I was mentioning about this Indian project on the hydrogen powered train. This basically hydrogen storage. Right now, I'm not clear whether it's a liquid hydrogen or gaseous hydrogen. I guess it is a liquid hydrogen, and which is then fuel cell based vehicle with then battery storage capacity is 1200 HP. So far nobody has done 2200 HP of hydrogen powered vehicle. Is somewhere around 800 to 900 if I am right. So these engines were recently tested and it going to run between Sonepat and some station very soon, which has been already planned last year. I don't know, something is happening, but this has been tested officially in July successfully. Okay. Now, coming back to this hydrogen, there is also one more area very promising, probably maybe aware, somebody must have not aware, that the future of solar panel is going to
Hello,
be
sir.
changed. Hello.
Sir. Sorry to interrupt you, sir.
Yes.
Slides are not going to be changed.
Hmm.
It is
Hello.
stuck over the video.
Yeah. Want to replay that?
No.
Ah.
Uh, we are not able to see your presentation. Just
Oh,
video.
okay.
Video screen is there only.
So now the screen is visible or not?
Screen is there, but the slide is not there.
Okay.
Also, some of the
Let me test.
participant ask
What?
regarding the audio about this video.
Okay. So I had
Yeah,
an issue. I
just
will.
please.
Yeah.
Yes,
Okay.
yes, sir. Please start once again that video with audio.
Maybe I will go back and then at the end I will come back if it is a time
Okay,
thing.
no problem.
Okay.
Yes, sir. Yes.
So
Sure.
let me stop sharing and then again restart it.
No problem, sir. You can carry out your presentation. There will not be any issue. We will see at the end of the session. Hello, sir.
Yeah, good evening all. Due to some technical issue, our current speaker is not in the meeting. He is joining the meeting again. Please wait for a minute. He will join again.
Sir, now you are in, sir. Yeah, yeah. Yeah, it
Okay.
is visible now. Yes, sir. Yes, sir. Yes, sir.
I hope you can able to see the screen.
Yes, yes, sir. Yes, sir. Yes, sir.
Okay. Yeah. Okay. So now, just a minute. Is my audio clear?
Yes, sir. Yes, it is clear.
Okay. Right. Just a minute. Okay, so this hydrogen solar panel is one of the very promising area. Right now, we know that the existing solar panel can produce um, uh, power generated from the sunlight. But if you have a combination of something so that it can produce the electrical power during the sunlight during the daytime, and in the afternoon time when there is no sun is not there in the evening or night time, it produces hydrogen. It's a combination. The morning it will produce electricity, in the evening it will produce hydrogen. So this combination of hydrogen solar panel is what now is going to be very future. In fact, many people who are proposed to go for solar panel are waiting for this technology, which are already come up, not in so effective, but methods are coming up. Many methods are there, hydrogen based coming. So here the hydrogen based solar panel is nothing but it's a normal solar well. It will produce electricity from the sunlight, store it in a battery, and during the night time, during the dampness or the moisture coming from the from the atmosphere in the night, that atmosphere, the moisture content from which you use the stored electricity to do the electrolysis process of splitting hydrogen and oxygen. In that way, you can get the hydrogen and store in the thing. So if you have the solar panel large enough, it can produce higher electrical current in the morning, and you store as a hydrogen in the night, which is again can be used when there is no power consumption is there, so it can also again. So it is a very combination of process. It's like capture and conversion. The panel will absorb the water vapor from the air using specialized membrane in the night, okay, or it do the electrolysis process by splitting this water molecule from hydrogen and oxygen. In fact, both the hydrogen and oxygen both can be used as a separate. It can be captured and stored as both as a hydrogen and oxygen, or you can either oxygen can be released into atmosphere. So all these combinations are possible by which we can produce the clean green hydrogen using an existing photovoltaic cell. And there can be two separate methods are there. One is that you have the photovoltaic electrochemical water splitting is one method which can generate a produce electrolysis process, like what I was explaining. Then other one is the photo electrochemical PET cells, which is a photocatalysis, that the solar cell itself will have a kind of a special membrane which will have when you expose to sunlight directly trigger the chemical reaction. Whatever the stored water molecules split there and then get the energy. See, basically, like a water sponge would have been collected the water molecules in the night, and during the daytime it gives out the photoelectric because of the current whatever produced from the normal solar cell will be used for producing the hydrogen also in addition to this normal power. So these are the two separate process is there, and both are upcoming and some of them are already installed, and each panel can produce up to 12 kgs of hydrogen. So depend upon the size, it's a typical size of whatever the standard size we have. One panel is equivalent to 2 feet by 6 feet size, and this will give 12 kgs of hydrogen in addition to the electrical power. Okay, so I have a small video about that. Can you able to hear the sound also?
Sir, we can see the video.
It's not there.
Can you able to hear the sound?
No,
Awesome.
Huh?
no, sir.
Yeah. Okay, okay. Then I will tell them.
सकते हैं, लेकिन हमें इसकी ज्यादा जरूरत
Yes, now it was audible.
Is it audible? Okay, just you can see the video. Just pause away.
Sir, right now the
Yeah.
audio, we can't hear the sound.
Okay. Okay. Then some of the things are written. I can use it. Yeah.
Yeah, you
Okay.
can move ahead, and at the end of the
Okay.
session,
Right.
probably
Okay.
you
Yeah.
can.
Otherwise thing. So now going back to the basic summon substance in the video is that you have the material which can absorb moisture, and with the electrolysis process, for which you need a power which has been stored in the previous in the daytime is used for separating the hydrogen. So basically the combination of electrolysis process and the solar cell is what this hydrogen solar cell is that. Okay, now coming back to surplus energy releasing, because it's moving away from the hydrogen a bit, but it's also a very clean energy. The thing is that we have a lot of windmill, thermal power plant, nuclear power plant. These plants, once you start, it's very difficult to stop it because it runs depend upon the thing. It is very difficult to stop it, and it takes a lot of precaution to do that. So when there is a change in the requirement pattern of the electrical power is there, for example, the winter season, the consumption a bit reduced here in India. So the windmill, thermal power plant, everything have to go on. But if there is a mechanism to use that atmospheric air is in a liquid form and store it in the liquid form, and then whenever it is required from the higher load is getting more, then you use the liquid air, evaporate the liquid air, and you know that we already seen 1 liter of liquid air will go to 760 times the gaseous content. So this high pressure gas will run that turbine the way it was thermal power plant or nuclear power plant where the steam is running. The same place, instead of steam, that high pressure nitrogen will run the turbine and the electric current can be moved. So whatever the electrical power which have been unused during the extra sources is get captured in a liquid form and reused whenever the demand is more. So this process of charging, storing, and discharging is what we call it as an liquid air energy system, LAES system, LAES. So very fine. So it means that if we store it and then reuse it, we can get up to even 65 to 75% of the power which otherwise would have been gone waste because it has been unutilized. So by doing the round trip efficiency of even 65, now we also have 75% availability is possible by which you can keep that high pressure store. So I have a small video where that there is a small bottle is filled with the liquid nitrogen. We have some nozzle, tangentially we have made some nozzle. I just again don't worry about the sound. Just see that thing. So when the liquid nitrogen is immersed in the water, which is a hot fluid compared to liquid nitrogen, the liquid nitrogen evaporated so rapidly, and we have made some two nozzle at the side, at the tangentially. The high pressure gas is coming out through that nozzle and making it to spin. So this is how that you can see the power of liquid nitrogen, which can drive a vehicle or drive a impeller to produce a current. So this is what exactly it does in that LAES system during the discharge phase. So it be nothing but we have an air get compressed with an extra power available from this source and gets liquefied in a liquefaction process and is stored in a liquid air system. So when you want to liquid to evaporate, you need some energy. So what they do to evaporate the energy, we pass that liquid through the compressor, and then compression heat is removed, and that actually the heat storage is being used to expand this evaporation process, which will go into air. If it is not required, you can have an external heat also, by which we can have, it's no geological limit. It can be put in any places because it doesn't need anything, because power is available from the windmill or the solar power, and atmospheric air is available. You put on liquefaction plant and a storage tank. It can have anywhere it's possible, and you can scale up to anywhere. And within 3 years, we can have it. And it's a very mature technology, and a lot of things are coming up by which you can have the surplus energy is stored in the liquid and takes out whenever that requirement is there. So where you can put this thing, whenever that oxygen and nitrogen are separated, you can store it nitrogen area, or oxygen can be used for the combustion process. Nitrogen can go into the fertilizer project. When there is a nuclear power plant, excess electricity can be used to liquefy the air, and then liquid nitrogen industry. So these are various areas where you can do it. So I come to the final part of my talk. It's nothing but this liquefied natural gas, which we know that it's liquefied at 115 K minus 160 degrees Celsius. So this is one of the area where you can do. So we'll see in the Asian scenario why this liquid nitrogen gas is available, because it's compared to fossil fuel, it's reasonably better. Okay, the CNG gases or liquid LNG gases. So India has a requirement of 86 megaton per annum. And then you see all other people are much lesser and that thing. So LNG, and India is importing quite a large amount from thing. And all the people want to reduce the carbon emission by this by 2030 by reducing this one. And we have another thing. Facilities are there. India also exporting here now large amount of liquefied natural gas, but slowly once that energy and green energy is available, hydrogen available, will switch over from here. Okay, so India is the fourth largest gas consumer in terms of LNG, and we are importing a very large amount, and 6 to 7% energy consumption is keep increasing. Government is increasing the energy consumption because the alternative to fossil fuel is next reasonably better choice is this one. Despite energy thing, we have to imported gas we have to import it large. So we need to have pipeline developing into national grid, which we are going to see in here. So we see that for last 10 years, that it has gone up tremendously high, about twofold of consumption has come up in terms of LNG consumption is there, and we wanted to go 6 to 7% every year. It is increasing in the large. So how do we go it? So we have a large number of liquid nitrogen gas terminals across India. So we see all the terminals are all along the border because we are importing and then storing it at the wherever that ship movement is there. And these are the green color, these are all operational, and these are all proposed LNG terminal is for storage and distribution. Now, all these things are available here, and the usage of LNG is throughout the India. How do you do this thing? So India has come up with a better choice of all the filling station or import requirements are happening here, and you laid the pipeline throughout the India, the large pipeline, so that whatever you get it imported from here, it transferred through the thing instead of the road transport. So we have existing 16,000 kilometers already available, and we wanted to jack up by another 100% within few years, and 8,000 are already under construction here. So if you see here, the quantity of LNG what we produced per ton per day and in operation, under construction, under planning is going in a very large scale up, so that in future that everything can cap up here. So if you see the cost in the whole operation, is exploration is one, purification is one, shipping is about the and storage. So what we are now adding is the cryogenics is also used here. When the large storage is there, it keep on evaporating. So what we do, we put some cryogenic application to re-liquefy the boil off gases, so that the temperature is maintained lower and lower, so that everything becomes the boil off is reduced. Otherwise, you allow to vent it and throw it out. So by which using the cryogenics, we can recool, or the regasification by using cryogenics, we can save a lot of things. So the 15-25% of the cost in the whole process can be reduced a bit. Okay. And this is about the purification, how you do. Of course, here also cryogenics is there. How you separate, how you degrade, dehydration, where you remove all that adsorb the hydrocarbon, then you removal of condense and cool with the cryogenic fluid to remove the lot of impurities. Then the purified is stored and storage and transportation. So if we not to say that actual application of LNG is that you have a ship to ship transfer. LNG comes in the offshore, you transfer here, from ship to ship, it transfer from jetty to ship is possible. And we have a boil off of 0.15% per day, which is went to atmosphere, which is what re-liquefied using cryogenics. So a lot of cryogenics coolers, refrigerators are available to have this and then recool it, so that avoid the wastage, because 0.15% of the large volume is quite substantial. Then we have a lot of terminals are there. Whenever it is the ship You come here and we have laid the pipeline, which is all the actual photograph what we have been using it here in various location. Like the marine engine, which uses a large quantity of diesel, is now switched over to LNG. So we have an LNG powered engines are available where we store the LNG in the ship, which is going to be the system in the rail locomotive, whatever, which is already there. It is already in place. And these are the LNG facilities at various locations, come from coast to the seashore where it gets stored and transported. For example, this one is from the large jetty. You have a pipeline to the shore where you get loaded, and how you offload that, the track offloading is done or filling from here. So many options are available, like the local storage where you can store it at the ground level, at this road level, how this can be done. A lot of things are all already available and in place at in India. And seventh thing is an automatic plan, which local vehicle, not only the local bus and everything. If I want to go to CNG, we need to have a large filling station every now and then, so that we don't need to run around for LNG for refilling option. So we have, I mean, lot of things is happening. At every 250 kilometers, they used to have a filling station. Like these are the major truck movement is being identified, and these routes are being developed with a large filling system and Inox CDA. So one of the people who well work within manufacturing, fabricating large cryogenic tanks and storage application also come up with all these things. Like in a truck, if you want to have LNG, these are the vessels it can you can store and connect it to a lake, and from the filling station, everything can be done. So this is overall about the whole LNG as a fuel. And I come to end of my lecture, and thank you very much.
Thank you very much, sir, for your session. As you have included all physics, chemistry, chemical engineering, refrigeration and air conditioning, cryogenics, then energy engineering, hydrogen. This is a very nice session and presentation also.
Okay.
Okay. I will ask to audience any question. Please give the access to all the audience.
Can you
Just
stop my scare? I could not stop scare. It goes out of it.
okay, just a minute, sir.
Stop the sharing, please.
Sir, you need to stop from your side only.
Okay, okay.
You can stop. Yeah.
Hello.
Yes, sir. Yes, yes, sir.
Okay.
Yes, sir. Yes, sir. Yes, sir.
Okay.
Now from
Yeah.
Audience, Dr. Dinesh Kumar, if you have any doubts or questions related to the session, you are free to ask.
Sir,
Yes.
Yeah.
Yes, sir. Yes, sir. Yes, go ahead.
good evening, sir. Sir, hydrogen fuel is highly flammable and it is very dangerous to use in automobile. So, in place of that, can we use DMFC, that is direct methanol fuel cell?
See, the safety part is there in all the places. Even the petrol engine also has the same problem. Okay. But if it is in a cryogenic form, it is not explosive. Obviously, when petrol leaks out, whatever the problem happens, will same thing happen in the hydrogen gas also, or the liquefied nitrogen also. As far as the safety is concerned, it exists in all the modes, including the mode what we are using it. But the safety precautions and the safety methodology and safety standards have been so rugged and have been proven and highly reliable that you don't need to have such a kind of a problem. Of course, when I was mentioning the hydrogen within a very high pressure 700 bar, which again is an issue, but to save that only have to have a liquid at a little reasonably higher pressure. Can you give me access to my camera?
Yes, sir.
Yeah.
Sir, so in place of hydrogen, can we use direct methanol fuel cell, which is
Anything can
much
be
much
anything can
safer?
be used. Anything can be used. For the LNG is more like a methane or the propane, butane kind of a thing only. But methane as such a fuel, because that is not the, I mean, how do we get the methane again is a problem. You don't get methane directly. For the CNG, you get directly. So there should be a cost-effective methodology is there, purification of methane, which may be used in rocket fuel nowadays. So it is not an apple to apple comparison. Yes, if it can be used, yes, it can be used, but at what contest?
Yes, any other question? Sushil Sathe, you are just raising the hand. Yes,
Can you
Yes,
give
yes.
me
Good evening,
camera
sir.
access?
yes,
I'm
yes,
not able
yes.
to start it.
Sir, I have provided the access to your camera also.
We couldn't access your camera. That's what your video is. Okay, maybe some issue.
Go to Teams and okay, no issue. Sushil Sathe, you are free to ask the question.
Yes, sir. Yes, sir. Am I audible?
Yes, yes.
Okay. My just having an issue is that whether that hydrogen vehicle is nothing but the invention. Hello.
Can you repeat the question?
This hydrogen vehicle, if suppose it will be quantum level, if it is raised, then we can say it is one kind of invention.
It is not the inversion because to have a quick convertibility. So tomorrow, if the government says there's all the petrol engine, no more petrol station, that the changeover. See, the same thing happened from the CNG conversion also. So existing vehicle to CNG vehicle. So this conversion, if it happened, there will be it should be quickly possible and cost effective without changing much into the engine side of it. So that is how the hydrogen vehicle IC engines have come into picture. If it's not going to be a fuel cell based vehicle, it should start from the scratch.
Okay, and at quantum level, what period we are expecting that this hydrogen vehicle will run on the road?
Yes, I guess that the conversion to IC engine, hydrogen powered IC engine is what quickly take off, considering the Indian condition.
Yes, sir. Yes, sir. We have heard that at Chennai, moreover, there are possibilities that more vehicles were running on the this particular invention, that hydrogen vehicle.
Yes, many things are coming up. I mean, maybe randomly, I don't have a very clear information that where it is now there, or it is an imported carbon. As such, now it is on the asset base. For example, I know that Bajaj was starting with the nitrogen powered engine, like a two-stroke petrol engine of an auto can be changed with an evaporation of liquid nitrogen. So I was, I mean, they are also in touch with me that hydrogen, liquid nitrogen is expanded the way what we see in the liquid air LAS system, that liquid nitrogen will be stored in the vehicle, and the liquid nitrogen will be passed through the radiator when the vehicle moves because of this atmospheric air, that it will get evaporated, the pressure will 760 times and it will run the vehicle. So that was the start point of it. So it's a similar way that conversing the world timing diagram is not a problem. Just change the cam operation and the fuel ignition part and the flow rate adjustment in the carburetor. This is the simplest thing we can do it, which has been possible to do, and this must have been done if at all if anything is there. It's no, I'm telling about a commercial vehicle which is comes in like that, which I don't have an idea.
Yes, sir. Yes.
Any other question?
Sir,
Yeah,
Yes.
good evening, sir.
good any.
Uh, while using our SI engine, if we are going to run it with the hydrogen, so what precautions or additions will have to take it? If existing gasoline engine, and we are
You're
going to
asking about
fire
the
it with the
density or the purity?
no precautions means we can fire it, we can run it, but additional precautions or what additions we have to do it in the existing SI engines, so that we can
In the
run it on
engine.
the we
See,
can run it with the
there are two, three
hydrogen.
options. One option is no changes at all, but the fuel quantity is Earlier it was about 2% or 3%. Now it's going to be 30%. So the valve at which that helium hydrogen is sprayed has to be changed so that within the given time of valve timing, you spray such a high quantity of hydrogen into the combustion chamber. So obviously this cannot be by a normal bigger mouth, or it can be by high pressure. So increasing the pressure of the hydrogen. So within the given time with a slightly bigger nozzle, you can push more fuel. So that is what the some connection changes will be there. And obviously the we know that power generated is 3 times than this one. So the wall timing should be much faster compared to the existing IC engine.
So what will be the maximum pressure which we can keep it if we are using the sequential
Okay,
injection?
I agree. I don't have much idea about it. I just with whatever the information, but don't take it seriously. Please cross check. I will also cross check from my end. It's something like about 6 to 7 bar at the gas at the injection point.
For the same nozzles, which if you are using the CNG fuel and it is having the attachment of a CNG injections, the sequential injection, and in that if I added the
Quite possible because unless we know that mass flow coming into the time within the same nozzle possible or not, because we have to do some calculation. It's not something like nozzle is there within the time. Wall timing is also adjusted. It is, for example, the fuel injection mode is something like 0.8 second. So 0.8 second is whether you are going to increase or decrease. If it will get increased, then you will have a combustion, you will have problem. You will have timing will be less. Obviously, it has to cycle time is fixed. So where we are going to have more, where you are going to, which will get affected with the less one. Obviously, all the combustion should go out, otherwise the moisture will set into the thing. So the timing should have exhaust valve should be more. So there's a combination of those things. So it's altogether automobile industry technology. What I was given is the possibilities of the, of course, I have also a calculation from that website, how you do the wall timing and everything, but some substances is increase the mass flow of fuel, decrease the mass flow of air, or make it equal, and adjust the existing wall timing to come with the record of 85% of your existing power. So power will be little less for that change with much changes. If you want to increase, obviously the bore size has to be increased, and also wall thickness of the cylinder has to be increased because we have to have a more pressure.
right, because with the increase in fuel, what happened that it will become red hot exhaust lines. They are becoming red
You
hot.
lose the fuel. No, if see all these wall timing need to have the fuel efficiency. So fuel efficiency, even complete combustion has to happen. If it is not there, you will have a wet combustion. So you will have more fluid. So every time you will keep on adding, then will lead to a knocking of engine. If the X quantity comes in, only delta X is combust and partially it is stand there. And next time also the X going to come up. Then delta X will be 2 delta X. So they keep on accumulating. So you can't have a free will of adding more fuel. What will happen? Less fuel. So fuel has to combust, and combust vapor has to go out. This is a basic line. How you adjust with these three is what.
Yes, sir. Yes. Okay, sir. Thank you, sir. Thank you.
Hello, sir.
Yes.
What are the safety precautions we have to take if we are using hydrogen in IC engine?
Just mentioning the previous thing, the safety part is that you are handling a very high pressure. And that very high pressure means that valves all should also be like that. When there is a venting will happen or some leakage happen, how quickly you vent it and how safely you can vent it. Or you can have kind of a medium in which it will vent not directly to atmosphere, it went through some kind of an metal layer so that it gets nullified, doesn't connect with the catch fire and kind of. So these are the techniques. But if it's blast, what will happen is same as what will happen to CNG, what will happen to a petrol tank. That remains the same, but the enough precaution and safety standards are already in place. And how much is to be done, right from the cleaning, how the nozzle, how the valve connection, everything is all been pre-designed, and this we have a standard called the PISO. Okay, so like our explosive unit at Nagpur, they lay the standards of what are the precautions should be at the filling station, connecting station, before connecting, how the pipeline should be vented. All the things are all pre-laid procedure. There are enough safety precautions are there, but what will happen is if anything, any kind of an unforeseen happen, is same existing in the current petrol or the CNG. So there is no change. Safety is not removed.
Thank you, sir.
Hello, sir. Hello.
Yes, yes,
Am I
yes,
audible?
yes, yes.
Yes, sir. Thank you, sir. I want to ask, we can use hydrogen as a fuel in the automobile by two ways. One is using hydrogen as a fuel in combustion vehicle, and as a fuel in run by fuel cell. So, out of these two ways, which is the most efficient one and most feasible one?
Most feasible is that most, I will not go feasible, I will come back to that. Most better way in terms of safety and other thing, that we can go for the fuel cell vehicle where you don't need such a high pressure for these
Okay.
fuel cell to happen, the fuel cell reaction to happen. So if I don't need to have a 700 bar pressure unless I wanted to take it for a longer run. So for example, if I have a filling frequency so fast, or if I have a more filling station, I can have a less pressure there. Fuel cell doesn't need more pressure. Whereas that IC engine needs certain high pressure. So we need to have both these things here. But to this thing, more optional way of running is a fuel cell based vehicle, which is a clean vehicle and doesn't have much. And then the conversion ratio, everything is much better compared to IC engine. But IC engine is quickly convertible with the existing scenario. Ideal is would be the fuel cell vehicle, and basically it's a hybrid vehicle of electric companies. So if you don't have, you charge it and you run it with your fuel cell. You start with electric and switch over to the fuel cell based vehicle, run it. The moment the fuel, whatever the capacity stops, then the switch over to electrical vehicle. So this what already happened, because I mean, I was earlier using Maruti LPG Duo. So it starts with electric petrol and then runs with LPG, but there is also forcible start on LPG also. So those kind of things are all electronically possible.
Oh, okay, sir. Another question, sir. While we are using hydrogen as a fuel, that too in the liquid under very high pressure and in liquid form, so we must implement some cryogenic system to keep it cool and under high pressure, that is in liquid form.
As per the
But in
user
case
is concerned, as per you are saying that what you need to learn.
I didn't get, sir.
Huh?
I didn't get, sir.
No. Your question is that if your storing is what you have mentioned about the current. Can you repeat the question?
Yeah, I was saying like while we are storing it in high pressurized liquid hydrogen form, in liquid form, so we must use a cryogenic system to keep it liquefied. Am I
Okay.
right, sir? And
Okay, I got your point.
in that case, if we are using hydrogen as a fuel in the car, and that too under cryogenic condition, so we must keep running that cryogenic system even if the car is not running for about 10 days. So who is going to provide the power to that cryogenic system, and from where does it get?
Okay. So there is no cryogenic system in the vehicle. See, this cryogenics, somewhere it's getting liquefied. For example, you have a petrol pump machine, you are giving the liquefied hydrogen, and the liquefied hydrogen is stored in your vehicle in an insulated tank, which I was showing one of the guide, which is the multi-layer insulation tank, which is vacuum jacketed tank. So the heat inlet to the tank is very, very minimal. Of course, there is some evaporation will keep happening, but typically, when you store it and doesn't use it, within 90 days, you will lose everything. So 90 days is what your storage is if you don't use it. So you don't need any cryogenic system. It's just a storage system. A cryogenic storage tank, which is nothing but a vacuum insulated tank with multi-layer insulation to reduce the radiant inlet plus the safety valve. So you don't take any cryogenic system along with it. Is that clear with you?
Yes. Yes, sir. Yes, sir.
Yeah, okay.
I hope everything is clear from participant side. I would like to thank sir for your nice session and question answer session also.
Yeah, thank you
Yeah.
very much. In case if any other questions also there, they can, I would
Yeah.
love that they can send it to me. I will happy to answer it.
Yes, sir. Yes, sir. Sure, sir. Yeah. Yeah. Yeah.
Okay. Sure,
Okay,
sure.
sir.
Thank you very much, and thanks, Army College, for the nice opportunity. And I
Yes, sir.
hope I have fulfilled your requirement, even though
Yes.
I wanted to touch upon all the thing in with an emphasize with cryogenics. So that was my talk about it. But these are some of the area where cryogenics is also actively used. So we thought the more
Yes.
thing, and I'm sure that it fulfills your requirement.
Yes, sir. Yes, sir.
Yeah.
Okay. Thank you, sir.
Thank you very much. Thank you very much.
Yes, yes, sir. Yes, sir.
Yeah.
Yeah. Santosh sir, are you there?
Yes, I am very much here.
Okay, okay, sir. Now I would like to introduce our second guest, Dr. Santosh Chavan, General Manager, Research and Development, JBM Green Energy System Private Limited, Gurgaon, Haryana. He completed his PhD from National Institute of Technology, Karnataka, MTech from VTU University, BE from uh, Vishwesvaraya Technological University. Dr. Chavan drives the R&D strategy, new product development, and compliances with the global safety standards while leading high-performance engineering team. His work reflects strong technical leadership, deep material understanding, and proven capability to deliver the innovative, cost-effective, and reliable energy storage solution for EV and grids and hydrogen energy. So I would like to share. I would like to ask Dr. Santosh sir. Can you share your screen? The stage is yours now.
Yeah,
Yeah.
yeah. Do I need to switch on my camera? Hello, everyone. A very good evening to all.
Please unmute yourself.
Okay. So
And
just
now it is
okay.
audible and we can see
Yeah,
your screen also.
yeah. My presentation is visible, right?
Yeah, yeah, yes, sir, yes, sir, yes, sir.
Yeah. So very good evening, all. So it will be a great opportunity for me to interact with you guys. So I will be going to discuss next 1 hour, approx 1 hour, on the topic of green hydrogen for sustainable future, prospect and challenges for energy-based applications. So let's begin with the global energy and climate context. What is happening globally? This will be a overall global perspective discussion rather than focusing on only India perspective. However, India's perspective, all credentials will be considered, but it will be a broader view. So uh, global energy contribution, specifically with respect to the global hydrogen demand trajectory, we can see in It is gradually increasing since from 2019, then 2021. Here you can see. Let me choose my God, 19, 20, 21, and here these were the traditional applications like industrial applications, steel manufacturing, and other things. But recently, the hydrogen is getting utilized for new applications as well, like transportation, power generation, and other things. So the hydrogen demand globally is 97 million tons in 2023, and which was the less than 1% being low emission hydrogen. So the CO2 emission uh, was 920 million ton uh, reduced in 2023. The emission from hydrogen production in 2023 equivalent to the annual emission of emission and France combined. So investment pipeline, the announced investment in hydrogen projects through 2030 will be 75 billion, having reached the final investment decision. So there is a huge investment happening globally on hydrogen production, hydrogen generation, hydrogen storage, and hydrogen utilization processes. So let's understand why green hydrogen and why now, right now, why we are talking about the green hydrogen now. So what is the need? So the need is definitely to save the climate, to reduce carbon footprint, and to uh, make our energy generation with zero carbon or zero carbon footprint. So there are different reasons, and there are global scenario or situations like climatic changes happening, global warming, all these climatic conditions indirectly pushing us to move towards the renewable energy source or green energy sources. So when considering green hydrogen utilization, the major consumers are steel manufacturing companies, chemical manufacturing, then shipping, aviation, which requires molecular solution where direct electrification isn't feasible. Then renewable integration, which enables high variable renewable energy penetration through electrolysis, load flexibility, and utilization of curtailed power. Then policy momentum, European Union European Union Renewable Energy Directive 3 has released, and in US it is Reduction Act. By using the different government policies, even Japan, Korea are monitoring the hydrogen production and utilization by providing various incentives or various tax benefits uh, at industrial and commercial level. Then seasonal storage, terawatt hour scale energy storage capabilities across weeks or months, complementing short duration batteries. So currently, lithium ion batteries are also growing. Parallelly, hydrogen energy storage uh, structures also parallelly getting developed. So what are the key benefits of developing the hydrogen? Specifically, green hydrogen. So first of all, it will produce zero carbon at the point of use because it produces water vapor as the only emission. It is versatile energy carrier for multiple applications. It may be like I mentioned, steel manufacturing, chemical, shipping, aviation, transportation, power generation, energy storage, likewise. System flexibility through sector coupling. We can couple this system with any of the applications. Wherever it is required, we can directly integrate with the existing system. Leverage existing infrastructure with modification that gives the extra advantage of uh, hydrogen utilization and enables deep decarbonization pathways. These are the key benefits, whereas equally there are current constraints. There are some challenges still exist to develop this technology. The basic the problems or challenges are cost gap versus fossil fuels. The cost gap approximately the the cost of hydrogen production per kilo is $5 to $7, whereas the fossil fuel, petrol, diesel, other gasoline are $1 to $2 per kg. So in today's scenario, the hydrogen production and utilization cost is higher than the conventional fuel. So nobody want to adopt or nobody want to go for higher or more expensive fuel side. So infrastructure deployment lags the production because there are not so many infrastructure or in industrial investments happening, or we don't have sufficient infrastructure to produce the green hydrogen. Then water requirement, water to produce 1 kg of hydrogen, we need to uh, waste 9 to 11 liter of water. So this is a huge quantity because if you are utilizing millions of water, millions of liters of water, then it will be difficult to manage. The standard and certification harmonization, there are still the technology is underway, so we don't have any specific standard or certifications to which can regulate the standard or critical limits of the process and utilization. Up to what pressure we can store, like in vehicles, transport applications, there is a certification body. It sets some safe criteria for utilization. So beyond that, we should not use because it may give adverse effect. There may be a mishappening or some accidental cases. So standard and certification is must. There is no strict or defined standards yet developed at government level. And technical efficiency losses across the value chain. So this is the presentation roadmap. So now current scenario also it reflects in 2025 the market status is technology. We are basically talking about the technology, production method, and all those things. Then by 2030 it will be scale up phase, where phase one the initial investment and costing will happen. Then third stage around 2040 market will grow, where the major applications will be fuel cell electrical vehicles, aviation, maritime, then steel, chemical and ammonia industries, then storage and grid integration. So by 2050, it is expected to generate net zero uh, carbon footprint energy generation or hydrogen production. So key definitions and hydrogen color codes. I hope you already aware of this different color coding of hydrogen. Still, let me go through brief. And here I am presenting in a different perspective with cost. So there are different hydrogen types or color coding like gray hydrogen. The gray hydrogen refers to the hydrogen produced by using the fossil fuel available like methane gas, coal, or other fossil fuel. The methane gas, steam methane reforming, SMR, or coal gasification without carbon capture. This is the production method. And CO2 intensity. This see from this gray hydrogen generation, how much CO2 we are generating. The natural gas, from natural gas, if you are generating, you are generating 9 kg to 12 kg of carbon dioxide per kg of hydrogen production. If you are uh, producing hydrogen from the coal gasification process, around 18 to 20 kg of carbon dioxide will produce per kg of hydrogen. And the typical cost involved is 1 to $2.3 per kg. So along with this, there are Some key characteristics. Currently, this gray hydrogen production dominates the market because this is quite old technology. It is mature enough and sufficient infrastructure have been established already. And the most undesirable part of this technology is high carbon footprint, which contributes to the climate change. So this process is mostly used, still it has higher carbon footprint. So next method is blue hydrogen. Next color code is blue hydrogen, or we can call it as low carbon hydrogen production method. Here, fossil fuel based process with carbon capture and carbon storage or utilization method is used. So, the hydrogen is produced from the fossil fuels itself, but the CO2 generated is again captured and stored or again utilized. So, carbon captured and utilized. So, by utilizing this carbon dioxide, we are able to limit the CO2 production to almost 1.5 kg to 5 kg per kg of hydrogen production. And carbon capturing will increase slightly the cost of hydrogen production from 1.5 to 3.5 dollar per kg. So this method is used around 70 to 95% carbon reduction versus gray hydrogen. So almost 70 to 95% this carbon dioxide production is reduced. This leverages existing natural gas infrastructure, then requires carbon dioxide transport and storage solution. Then coming to the green hydrogen. Green hydrogen is produced by using water electrolysis powered by renewable electricity. So water electrolysis specifically by using renewable electricity, solar PV and wind hydro. If we are using the existing power plants like thermal power plant, nuclear power plant, and fossil fuel power plants for splitting the water, then that we cannot call the green hydrogen. So this has to be developed purely from non-fossil fuels. So here the CO2 generation is very, very minimal. That is 0.5 to 3.5 gram of CO2. But the disadvantage is its cost of production is slightly higher, like $5 to $7 per kg. So it has some advantages like zero direct emission during production. Cost depends on renewable electricity price, rapidly declining cost trajectory. So right now it is $5 to $7, but it is expected in upcoming years, 5 to 10 years, the cost will go down to $2 per kg or even less than that one. So the last one, low emission hydrogen. This hydrogen will it will meet all the pathway, jurisdiction, intensity, and threshold. It will meet all the criteria or the regulations set by the government or the certification body. Like European Union has set the carbon footprint should be less than 3.38 gram per kg of hydrogen. US has set 4, then Japan 4.5. This low emission hydrogen will meet these criteria. The green hydrogen is produced within this limit. And the cost of production is 3.5 to $7. It has a regulatory classification rather than the specific process. Many includes like biomass based or nuclear powered electrolysis. This enables global trade through certification scheme. So now let's discuss electrolysis technology overview. Just I want to interrupt here. If these things have been already covered in the previous session, just you can let me know. I can skip those slides because I don't know what has been covered. Electrolysis technology. So the basic electrolysis technologies are the most common one is proton exchange membrane. So proton exchange membrane, the operating conditions will be 70 to 90 degrees, but it will be operated at very high pressure, that is 30 bar. The environment will be acidic and ionized water is required. The efficiency is around 65 to 70% lower heating value. Then electrical usage is 57 kilowatt hour per kg of hydrogen. Then fast response in seconds. So energy generation is very fast process. The energy will get generated within seconds. This is excellent for load following. If we are generating electricity for grid application, so whenever there is a power cut off in the grid, immediately we can switch on this, and within second it will uh, supply. It will get connected to the grid and it will supply the electricity. So that is the quick response advantage. So the capex required, capital expenditure required or capital investment required is around 1,500 to $2,500 per kilowatt capacity. So higher capex than alkaline. This is premium material as a PGM catalyst is used. Then stack life and durability. So how much it will be durable? How long it will run? So it will run around 40,000 to 60,000 hours of operation. And a replacement cost is around 11% of total installed cost. It will be around 11% of total installed cost. Then degradation is 2 to 4 microvolt per cell per hour. So market status as per 2024 is it is growing, deployment of around 25% of installed capacity, then preferred for grid balancing. As I mentioned, because of its fast response nature, it is used for grid balancing. So second is alkaline water electrolysis, AWE. So this is slightly high temperature condition operation. So here the temperature is 100 to 105, pressure is around 1 to 30 bar. In alkaline electrolyte, that is potassium hydroxide is used, uses less pure water. Then the efficiency also it is near to the PEM, like efficiency 60 to 70%. Electrical usage 55 to 60 kilowatt hour per kg. This has one disadvantage is slower response. It responds in minutes, not in seconds. So this is limited for part load operation. But the advantage is the cost is almost half of the PEM. So it is initial investment is around 800 to $1,500 per kilowatt. So lower capital investment is required compared to the PEM, and non-precious metals catalysts are used that can be used. So the stack life, the life cycle is also it is better than the PEM. It can operate up to 60,000 to 90,000 hours and longer lifetime than the PEM. This is more robust to impurities. So when talking about the commercials, 65.46 market share is captured by the alkaline water electrolysis. And larger deployments are happening globally. Almost 75% of installed capacity is almost alkaline electrolysis method only. So the third technology is solid oxide electrolysis cell, that is SOEC. This is slightly, we can say it is more industry specific application because the operating temperature required is 700 to 850 degrees centigrade. It is not possible for any other small scale application. So here pressure requirement is very less, like less than 5 bars. Ceramic electrolytes are used. Heat integral critical. So heat integration is critical because there should be some heat source which can supply continuous heat to maintain water temperature around 700 to 850 degrees centigrade. It is a big challenge. So the efficiency and response, its efficiency is higher than the alkaline water and the PEM, that is 70 to 80%. Then up to 95% waste heat can be used, or the after utilizing the heat, 95% heat will be rejected again, and its response is very slow. It will respond in hours, not in seconds, not in minutes. Then capital investment around 2000 to 4000, because this is main contributor is this thermal input, heat input. So the project cost will be 800 to 1500 projected cost per kilowatt hour, the high temperature material cost. So if when we are running, it is not just about the heat source. To sustain 700 to 850 degrees centigrade, the whole system should be developed with the high temperature resistant material. So we cannot use normal materials in this one. So that will directly influence on the cost of the installation, or initial cost of the production capacity or system. So its life cycle also 20,000 to 30,000. Thermal cycling limitation is there. We are unable to recover maximum amount of heat. Then seal and interconnect challenges, because there will be more leakages because at high temperature utilization. This is still under pilot and demonstration mode, and limited commercial deployment has happened. Less than 1%. So PM electrolyzer specs and efficiency in brief. I will not go in that much detail. So simple proton exchange membrane electrolyzer, how it works: the water will enter and electricity will be applied. Proton exchange membrane, and water will get split into water, hydrogen and oxygen. So this has very good dynamic response, high purity, compact design, and scalable. So electrical efficiency is around 57 kilowatt hour of electrical energy is generated per kg of hydrogen. So it is electricity, 57 kilowatt hour of electricity is consumed to produce 1 kg of hydrogen, and levelized cost of hydrogen, LCOH, is $5 to $7 per kg. Here LCOH means the cost of hydrogen production per kg for throughout the project, not only the initial stage, because throughout the project the production cost may vary. So the total throughout the project, the cost of hydrogen production per kg is called levelized cost of hydrogen, that is LCOA. So it will be around $5 to $7 per kg. So operating temperature, as we already discussed, 70 to 90 degrees. Then stack replacement is around 40,000 operating hours. Then operation and maintenance cost is 5% of total installed cost. Then the key advantages are rapid dynamic response in seconds, ideal for grid balancing, high current density, 1 to 2 ampere per centimeter square, compact footprint, then high hydrogen purity, 99.999% pure hydrogen we can generate. Then operational under differential pressure, direct production at 30 plus. Then alkaline, similar way, this is already discussed. Instead of PEM, the KOH, potassium hydroxide electrolyte is used. And this is the basic representation you already aware. So the operating temperature is 100 to 105 degrees centigrade. Then capital expenditure, system efficiency is 60 to 70%, and the dynamic response is bit slower compared to the PEM. The operational lifetime is 2000 to 90,000 hours. The market leadership, alkaline technology dominates the current green hydrogen market. This is largest revenue share in 2024 global electrolyzer market. That is, it is contributing around 65% of the global market share. Then SOEC, already discussed 70 to 80% with heat generation, heat integration, 700 to 850 degrees centigrade. We need to maintain. Then technology readiness level, it is 6 to 7. That is pilot or demonstration. Here, technology readiness level is divided into number from 1 to 9. So, where 1 represents initial concept level and design level thing, where 8 and 9 represents the finally full commercialization. So, it is in between the initial beginning phase and the final commercial phase, 6 to 7. So stack durability already discussed. Then path to lower LCOH, the cost of hydrogen production is expected to be 3.5 to $5 per kg. So the key advantages are highest electrical efficiency, potential for all electrolysis technology. Can utilize waste heat from industrial processes like steel, glass, cement. See, this is the unique feature of this system. Here, if the heat is readily available from the some other primary applications like steel manufacturing, iron has to be melted above 1500 centigrade degree centigrade. So after melting the iron, the waste heat is rejected to the atmosphere or it is recycled. So beside that, the same heat energy available in the source that can be utilized here. So glass manufacturing and cement manufacturing company also, they need bigger boilers to maintain or to supply the heat for their process. So those heat source, if it is already available, those can be used, and this will be most efficient for those applications. So potentially for CO electrolysis of carbon dioxide and water to produce synchro gas, lower electricity consumption due to favorable thermodynamic at high temperature. So LCOS breakdown, today's cost stack. Cost definition I already told. So the cost of hydrogen per kg. So in this cost, the electricity cost is involved, electrolyzer cost is involved, fixed operating and maintenance cost is involved, stack replacement. After its lifespan, stack replacement cost is involved, and the total cost of hydrogen that LCOH is around 6.5 dollar per kg of hydrogen production. So electricity is around 3.2 to 4.7 dollar per kg, and electrolyzer is 1500 to 1500 per kilowatt. And maintenance is 5%, tax is 11%. So baseline for LCOH, EM and renewables are around $5 to $7 per kg. So this number has to be remembered. The cost of hydrogen production now by till 2024 is $5 to $7 per kg. So technological readiness and deployment plan. So alkaline wastewater AWE technology is already around 8 to 9 numbers. So it is mature technology with decades of industrial deployment. Already it is installed, everybody is deployed, and it is readily adaptable technologies available. So its efficiency is 60 to 70%, lower current density than PEM. It dominates the market share, almost 65% it is captured. Then lower capex required than PEM. Established supply chain. So raw material supplier, electrolysis supplier, and all the part supply chain is established one. So there is no need to search for new sources or new suppliers to find the to get connected for supply. So limited dynamic operation. So then proton exchange membrane, its phase is also almost equivalent to the AWE. Commercial deployment scaling is rapidly growing. Its efficiency already we discussed 65 to 70%. Then rapid dynamic response. It is compact in design, stack replacement of 40,000 hours. So solid oxide electrolysis is around, it is in the halfway. Still, this technology has to be evolved. It will take bit time to get matured, and it should be available in upcoming 3 to 5 years. So here, as we discussed, the high temperature source is required, superior electrical efficiency, durability, and challenges being addressed, industrial weight heat integration potential. So wherever industrial waste heat is available, this technology will be more suitable. So next future technology is anion exchange membrane. So this is around technology readiness is 4 to 5 only. So it is still in early stage. So the technology has to grow up and reach maturity. So it is under development, under demonstration itself. So this has a potential of lower capex then non-precious metal catalyst is used. Membrane stability is improved. Limited field data are available because of non-deployment. This system is not deployed. It is still under development, emerging one. So the data is not available to make any decision. So manufacturing capability, global electrolyzer manufacturing capacity reached 17 gigawatt per year in 2023, growing to 25 gigawatt per year in 2024. So China accounts for 60% of global capacity. Significant underutilization, only 2.5 gigawatt hour output in 2023, 15% utilization rate. So manufacturing capacity could exceed 165 gigawatt hour per year by 2030 if all announced plans materialize. So several plans have been announced. It has to be, if all plans meet their deadlines, then we will be able to reach this target. So the deployment trajectory is seems current operational capacity is 1.75 gigawatt hour by May 2024 data. Project at FID stage is 26 gigawatt hour. Total announced plan is by 2030 375 gigawatt hour. Probability adjusted forecast is 90 gigawatt hour by 2030. So hydrogen types and use case fit where we can use that one. Again, we already discussed gray hydrogen, blue hydrogen, green hydrogen. Production method we already discussed. Then CO2 generation cost. The only new perspective here discussion is scalability and regional fit and infrastructure requirement. So for gray hydrogen, it is highly scalable with mature supply chain because this is already proven technology and many uh, solutions or establishments are happening and supply chain is readily available. Optimal in gas-rich region like US and Russia, Middle East. Not compatible with net zero target. With this technology, we cannot uh, meet the net zero carbon footprint target. So this needs established natural gas infrastructure, that is methane gas. So SMR plants typically at refineries, chemical facilities, because in Middle East, like fossil fuel, petrol and diesel refinery, the infrastructure will be readily available. Same infrastructure can be utilized for producing this gray hydrogen. So limited new infrastructure is needed. We can utilize the existing infrastructure. So blue hydrogen, moderate to high scalability, best fit where natural gases plus carbon dioxide storage available, like US, Gulf, North Sea. It is limited by carbon capturing and utilization and storage availability. The natural gas supply infrastructure, uh, The infrastructure requirement is natural gas to be supplied, CO2 transport pipeline should be there, geological storage site should be there, monitoring system for leakage should be provided for safety concern. Then hydrogen, green hydrogen, the high scalable, where renewable abundant. So here, where renewable energy are abundantly available, there we can prefer this one. This is optimal in region with low cost renewable, like Australia, Latin America. It is limited by renewable electricity available. If we are not having renewable sources like wind energy, solar energy, then this cannot be a practical solution. So renewable electricity generation is must for green hydrogen production. Then grid connection or direct coupling is required. Then water treatment or supply is required. Then hydrogen storage and transport. So from the methane pyrolysis, the new technology, this has medium scalability technology measuring the gas rich region with carbon market, then limited by solid carbon offtake markets, then natural gas supply, solid carbon handling and storage, heat supply preferably renewable, then it is limited commercial plants currently. So global hydrogen production status by 2023 and based on the 23 and 24 data, regional distribution of clean hydrogen production in million tons per annum. So China has operational million ton per annum. Then this is FDA construction. This is the construction line. What is construction? This is construction line, and this is announced by 2030. It is about to reach by 2030. So China's target, then North America target, then Europe target, the Middle East, Asia Pacific, Latin America, and rest of the world. So from this picture, we can think about the technology growth by 2030. How this green hydrogen production technology will swift off, how it will move. Size outlook by 2025 to 2050. So green hydrogen, from here you can see the this green line represents market size in billion. So $10 billion from 24 so up to 2030, it will reach $60 billion. If we consider this high adoption scenario, then it will grow by $70 billion. If we consider this as a medium, then also it will market will capture around 7.70 how much $40 billion. And if we consider conservative scenario also, it is $20 billion. So the market growth rate is 38.5% CAGR. Compound annual growth rate is 38%. Their market size projection is 7.98 billion to 60 billion between 2024 to 2030 market evaluation. Long-term demand for by 2050, the scenario million ton of hydrogen. High adoption will be 50 to 60, 500 to 600 million ton. Medium adoption for this, it will be around 300 to 400 million ton for conservative. If it is growing less than the expectation, still it will be generating 150 to 200 million tons of hydrogen. So investment trend and project maturity, how the how it will begin. So investment level, low, high, and project mastery. Early stage, the research will be research are conducted. Then pilot projects are developed. Then the scale is increased. Then it is commercialized. Then it is initially funded, and the multiple industries will be set up and scaling up for private equity, and full-fledged technology will flow throughout the world. So till now, for hydrogen production, the projects in pipeline are 1,572 projects globally available, with 434 projects having research FID or beyond. So it has crossed this region. It is under 4 to 5 number. Then having representing 7x increase in compared to the 2020. Committed investment is around $75 billion. This a 90% increase since 2023. So by 2030, supply outlook is around 12 to 18 million tons per year. So the hydrogen production is expected to increase 12 to 18 million tons per year. So regional leaders are the key players in India, within India and globally. So in India, public sector and government sector, the NTPC Limited is there, Indian Oil, Reliance Industries, Ministry of New and Renewable Energy, Solar Energy Corporation of India. These are the major players. And private sector, Adani New Industries, Larsen and Turbo, then Acme Group, Renew Power, Omium International. These are the key players who are investing in India. So for green hydrogen production. So in Europe, already 617 projects, almost 40% of global projects are acquired by the Europe. Then North America, 280 projects, around 18% of the global contribution. Then China has 1.15 gigawatt of electrolyzer capacity operational. So electrolyzer raw material supply for this hydrogen production is controlled by China. So globally, 65% of raw material is supplied from China. So emerging regions are Latin America, 8 million ton per annum planned by 2030. Middle East is planned 0.3 million ton per annum. Then Oceania, India is planned 40 gigawatt of electrolysis announced. So these are some global players in the air liquid, air products, Siemens Energy, and ThyssenKrupp, Bloom Energy, etc. So national strategy and policy lever. So to regulate or regularize the hydrogen production, the different countries have developed their national strategies. So European Union has some key policies like Renewable Energy Directive, Renewable Fuel of Non-Biological Origin rules, European Union Emission Trading System, EU Taxonomy of Sustainable Activity. These policies defines about carbon contract for differences. Quota of 42% industrial hydrogen from renewables by 2030. The policy is target. Then by 2030 target 10 million ton domestic renewable hydrogen production, 10 million ton renewable hydrogen import, 20 gigawatt electrolyzer manufacturing capacity, 50% renewable hydrogen in industrial consumption. These are the targets of European Union. They are planning to achieve this target by applying the policies, government policy. Similar way, United States has also framed their government policies. Then Japan, India also National Green Hydrogen Mission, Strategic Intervention for Green Hydrogen Transition Program, R&D incentive and pilot projects are initiated. Our policies may involve 2.4 billion total incentive package, production linked incentive. Like if we are willing to uh, produce green hydrogen within India, so there will be a great subsidies involved to it. So per kg of hydrogen production, there will be some incentives will be provided from the government. So mandate around 10 to 15% green hydrogen in refining and fertilizer. Availability gap funding mechanism. So government is readily aware. It is very keen to invest in the hydrogen production industry. So the target by 2030 is 5 million ton green hydrogen production per year, 125 gigawatt of renewable energy capacity, 100 billion investment mobilization, 50 million ton of carbon dioxide emission reduction. This is our main target. So cost reduction trajectories. So by 2030, what is the cost reduction? Currently, as we already seen in the previous slide, around $5 to $7 per kg of hydrogen production cost is changing. But as the technology is becoming more mature and it is more common and supply chain is readily available and technology is more accessible to the more people, then the cost of production will get reduced. So if we consider green hydrogen net zero emission scenario, the cost uh, the cost will reduce from $7 per kg to around $5 per kg. Sorry, it is yeah $4 per kg. So if we consider hydrogen by net zero emission scenario, lower possibility, then also it will be around 2.5 uh, dollar per kg. So this way we can understand the hydrogen production cost will get reduced as we move in the further by 2025, 26, 27, 28. By 30, the cost will significantly reduce. So LCOS reduction net zero scenario 50% by 2030 from $5 to $7 per kg to 2 to 4 kg by 2030. Gap to be unabated fossils like 3 to 6 per kg, 1 to 3 per kg. So this is fossil fuel cost. So the cost reduction drivers, what factors actually influence the cost reduction? So renewable electricity cost reduction. So if you are generating the electricity from the renewable sources like solar and wind, so we will be able to reduce the hydrogen production cost. So electrolyzer capex learning curve. So electrolyzers, if we are able to manufacture within India and locally, if it is available, then the cost will reduce. The efficiency improvement. So if our hydrogen production system efficiency is increasing, then also we can control the cost of hydrogen production. Then high CF, around 74% with hybrid like wind plus PV. So supply, demand and outlook. The hydrogen supply demand gap by 2030 million ton per annum. This is the optimistic scenario and the conservative scenario. So the announced supply is this. So probability adjusted supply and government production target 40 million ton. So announced by probable supply will be 48 to 49 million ton is announced, but 12 to 18 million ton will be achieved by 2030. Government target is 23 million ton. And the scenario analysis are further accelerated around 45 million ton. Achieved commitment is 30 million ton. Current trajectory is moving towards 20 million ton. And fading moment is 10 million ton. The regional LCOS differentials by 2050. So within India, North India, West India, South India, East India, the cost distribution of LCOH and LCOE, levelized cost of hydrogen and levelized cost of emission. So West India shows lowest LCOS due to higher renewable energy potential, overall cost reduction by 2050 due to emerging infrastructure scale. So coming to the transportation application, fuel cell electric vehicle technology and market snapshot. So the deployment of electric vehicle based on fuel cell or passengers car were highest like 45,000. This is in 2023 and 24. So buses, around 15,000 buses, then trucks, around 10,000, and other commercial vehicles, around 5,000. So global deployment is 90,000 vehicles, fuel cell vehicles on the road globally as of May 2024, with growth concentrated in commercial vehicles. Regional distributions are like China's vehicle are running almost 45%. South Korea's vehicle on hydrogen is 22%, Japan 15%, Europe 12%, and North America 6%. So available models are 160 plus. Then technical performance, it is 40 to 60%. The fuel cell stack efficiency with a driving range of around 400 to 800 kilometers and refueling time of just 10 to 20 minutes. This making fuel cell electric vehicles particularly suitable for heavy duty applications where battery weight becomes prohibitive. So as of today's technology, the this hydrogen fuel cell is more suitable for heavy truck and the passenger car application. So heavy duty truck fuel cell truck architecture. Here, the system efficiency is around 48 to 53% at highway cruise. Operational range is 400 to 800 kilometers. Hydrogen consumption rate is 7 to 8 kg per 100 kilometers. Payload advantage is plus 1 to 2 ton versus battery electric will carry more weight compared to the battery vehicle. Then power output is 180 to 300 kilowatt. So the total cost of ownership compared to the factor. So total cost of ownership is the total cost of the vehicle when it is operated for certain fixed interval of time. So if you buy the petrol vehicle and use it for 5 years, and if you uh, purchase a hydrogen fuel cell vehicle and use it for 5 years, then what will be the total cost? It comes with fuel refilling, maintenance, repair, rework, and all other points will be considered. Total cost of ownership. So vehicle cost is higher, 3 to 4x of diesel. Then BEV, battery electric vehicle, 3 to 4x of diesel. Diesel is baseline. So fuel energy cost medium is $5 to $10 per kg of hydrogen. Electric vehicle is low, diesel is high. Payload capacity, it is high, it is reduced and baseline. We are comparing with diesel vehicle. Infrastructure is limited. For electric vehicle, it is growing. And for diesel, it is mature. Refueling time, it is 10 to 20 minutes. It is for battery charging, it is 30 plus minutes. Then for diesel filling, it is 5 to 10 minutes. The commercial vehicle deployment is around Hyundai Accent 34-ton gross weight vehicle, 190 kilowatt hour truck are used for 350-kilometer range with 32 kg of hydrogen storage. Then Nikola tree is there. Hyzon heavy duty trucks are there. These are the different model trucks available. So aviation application. So sustainable aviation fuel. SAF market growth is from 2 billion to the 25 billion by 2030. It is almost of 65% of market growth. So hydrogen pathway in aviation is synthetic e-kerosene production pathway requires green hydrogen from electrolysis, CO2 from direct air capture or point source, Fischer tropes or methanol to jet conversion, drop-in compatible with existing aircraft and infrastructure. So direct hydrogen use uh, makes it advantageous technology compared to the old one. The liquid hydrogen fuel storage at minus 253. Hydrogen combustion turbines or fuel cells are used. Zero carbon emissions are advantageous. So next application is maritime hydrogen driven fuel like ships. methanol as hydrogen carrier. Global fleet adoption is 200 plus methanol fueled ships ordered globally. 9 vessels currently in operation by 2024. 40 plus new orders since 2023. So the ammonia and direct hydrogen use. Ammonia ready vessels. Actually, the hydrogen is stored in ammonia to utilize as a fuel. So ammonia ready ship orders higher hydrogen energy density around 17.6% by mass than methanol. Hydrogen can be stored in ammonia 17% more than the methanol. The liquid at minus 33 degrees centigrade at 8 bar pressure. But there will be a safety concerns. Toxicity requires special handling. Then hydrogen fuel cells, direct hydrogen application emerging in a ferry and short sea shipping, high efficiency around 48 to 53% compared to the internal combustion engine of 25 to 30%. Zero emission operation, water only byproduct. So as a byproduct, there is no smoke, only water is produced. So by 2050, marine fuel projections are expected to be ammonia 35%, methanol, e-methanol 30%, biofuels 20%, and others are 15%. So liquid at ambient condition simplifies the storage of hydrogen. Established production infrastructure makes it more viable. Easier bunking with existing equipment is more practical. Then dual fuel engine allows flexible and more reliable. So hydrogen refueling infrastructure. So hydrogen production and storage are the one part, and refueling is the another part of the technology. So we must have the refueling infrastructure to utilize the full technology. So current in India, approx in 2024, approx only 5 stations are available in India. By 2050, the target is 10,000 plus fueling station. The total investment is 8 lakh crore, that is 95 billion USD. Vehicle supported will be 5 million plus. Fuel cell electric vehicles is planned. So China is having 390 stations, South Korea 290, Europe 248, Japan 160 stations. So this is the refueling infrastructure is also globally growing very fast. So mobility market penetration forecast can be visualized here. See heavy duty trucks, heavy duty the fuels this hydrogen fuel cells are used in heavy trucks majorly. Almost 65% is contributing by heavy trucks. Second option is buses. Because of its storage tank capacity and ruggedness, only heavy vehicles are more suitable. Passenger cars are also using this, but if you increase the storage, tank ruggedness, and the because hydrogen we have to store in the high pressure, so higher thick or very strong material has to be used. Because of that one, the weight of the vehicle will increase and the efficiency will get reduced. So the passenger cars based on the fuel cell will be uh, lower number we can see. Shipping is gradually increasing. Is till now it is slowly increasing. By 2050 is expected to be grown more than 35%. Aviation fuel also it is expected around 30%. So steel decarbonization. So in steel industry, how the hydrogen utilization is distributed. Like India, 49.3 million ton, Iran, 33 million ton, Russia, 7.8 million ton, Saudi Arabia, 6.7 million ton, Egypt, 6.4, other countries, 32 million ton. This is DRI production. That is direct iron reduction. Annual global direct reduced iron production in 2023 represents around 6.5% increase from the previous record. So but the uh, production method is 68.5% gas based. So natural gas based direct reduced iron production is low carbon dioxide emission counts 68.5% of production, while the remaining 31% is coal-based with higher carbon intensity. So decarbonization potential of less than 0.5 ton of CO2 per ton of steel. So hydrogen DRI projects pipeline major different countries, which are the project and what capacity it is already running. Like in China, capacity 0.6 million ton per year is planned. Its status is operational since June 2023. The technology is Energeron ZR with hydrogen injection. Germany is working on capacity of 2.1 million ton per year DRI plant. Its feature is 10 megawatt electrolyzer integration. It will start mid 2026, partnering with Tinova. In Germany, another project 2.5 million ton per year. CO2 reduction 3.5 million ton per year is targeted. It will start by end of 2026. So Oman 2.5 million ton per year is planned. It is in under production and it will complete. The installation will complete by 2026 and in collaboration with Jindal Steel. Total 7.7 million ton per year is expected capacity from major announced projects. The ammonia and green ammonia. The current global production is 180 million ton per year. Only 0.01%, that is 0.022 million ton, is currently green ammonia, with substantial growth projected as decarbonization efforts to accelerate. So actually, the current green ammonia production is this line, but the actual ammonia production is this. This is not a green ammonia production. So hydrogen carrier properties are 17.6% hydrogen content. So the advantage is liquid at minus 33 degrees centigrade at 8 bar, establishing infrastructure high energy density. Uh, if infrastructure are well established, the energy density will be very high. Its disadvantage is toxicity is there, reconservation energy losses around 20 to 30%. NOx, nitrogen oxide emission also will be there. Production cost comparison around 2 to 3x or higher than the normal ammonia production. So green ammonia production, the cost will be 2 to 3 times. So refining and chemical clean hydrogen uses. So in refining application, current hydrogen demand is nearly 33 million ton per year, which accounts for 35% of global hydrogen consumption globally. So key refining process are hydrotreating, removing sulfur, nitrogen, and metal from petroleum feedstock. Hydrocracking, converting heavy hydrogens into lighter and higher value products. Then hydrogen intensity, 20 to 80 kg hydrogen per ton of processed crude oil is can be generated. Then chemical production and industrial hubs, chemical sector application has nearly 31 million ton per year and methanol around 12 million ton per year. So this process involves ammonia production around 180 million ton per year globally. Only 0.01% green, remaining is normal ammonia. So methanol production is 110 million ton per year. Hydrogen intensity is around 0.11 kg per kg of hydrogen per kg of methanol. So future e-chemical pathway is CO2 can be used as a feedstock feedstock to hydrogen storage, then circular carbon waste plastic gasification with green hydrogen can be utilized. Then industrial hub strategy can be adopted, which demands aggregation, then shared infrastructure. So the cross industries can develop a common infrastructure. They can utilize it for uh, multiple applications. Like different countries can combinedly develop a common infrastructure to utilize it. So implementation timeline and phasing. So how phase wise manner by 2050 it is expected. So by 2025 to 2030, phase one, which replaces gray hydrogen. Here it is expected to replace gray hydrogen in existing uses. Refineries switch to blue or green hydrogen. Chemical industry switch to ammonia and methanol. Early mobility pilots and demonstrations are happening. Initial pipeline repurposing projects for creating the refueling stations. The pipeline supply is underway. So in second phase, it is expected to be happening by 2030 to 2040. Then the scale of new applications, steel DRI, large scale deployment, maritime shipping, ammonia and methanol based ships will be produced. Then power sector integration for electricity generation to supply to the power grid that can be deployed. Then synthetic fuel production. Then in phase 3, 2040 to 2050, deep penetration and across the sectors. So this technology can be used in across all the sectors like aviation, transportation, energy generation, industrialization, and other things. So the sectors where hydrogen can be implemented is refineries and chemicals. Currently, gray hydrogen is used, which can be replaced with the green hydrogen. Then steel industries, which are adopting steel industry. Specifically, I mentioned the high temperature application, which are under pilot and demonstration mode only. Maritime, this is early adopters. They are still trying. Power grid application demonstration stage it is available. The key dependencies are the limitations. Why it is not growing so quickly is infrastructure. The pipeline infrastructure is not available, it is underway. Government policies are not fixed, and OEM manufacturing giga scale electrolyzing manufacturing industries are lacking. Then scale up facilities not available. Commercial hydrogen DRI are there. Fleet transition, the fleet transition like transportation vehicles immediately switching is like basically nobody initially uh, will be interested to move from one platform to another platform. Like right now, we are using all the fuel cell, petrol and diesel vehicles. If we and we are not interested to move towards electric vehicles because of we are not uh, having sufficient data to rely on the electric vehicle. So we are. It is basically it is not developing that trust. So same way, if you want to, if somebody comes and asks you, just migrate yourself from electric vehicle to the hydrogen fuel cell, then immediately we will say whether it will be safe, how I will manage, how I will maintain, how repair work will be happening, operational and maintenance, refueling, all concerns will come. So grid scale storage for grid application that will be also will be a challenge. Then this can be dedicated to hydrogen networks. Then developing hydrogen network is also a change. Like fuel stations everywhere, we are getting the hydrogen supply should be there. Carbon pricing and mass production. So grid scale energy storage with hydrogen So energy storage technology comparison, like pumped hydrogen, batteries, compressed air, hydrogen salt storage, and hydrogen depleted fuels. So storage potential is around 100 plus terawatt hour. Hydrogen underground storage technical potential is salt caverns and depletes gas fields essential for interseasonal storage in high renewable energy grids. So the hydrogen can be stored for interseasonal, like 4 months, winter to summer, summer to rainy season, it can be stored. So existing infrastructure of 5,000 kilometers operational, hydrogen pipeline globally available around 5,000 kilometers, which is significantly expanding through new builds and natural gas pipeline. System application is around 18 to 46%. Route trip power to power efficiency ideal for long duration storage. So power to gas and to gas to power efficiency cycle. So electricity we are supplying, then electrolysis is happening, then water splitting is happening, then it is again utilized in fuel cell and converting into electricity as an output. So total the efficiency of the complete system is getting reduced. So when compared to the battery storage, the efficiency, round trip efficiency is 80 to 90%. The round trip efficiency means if I have a battery and I am charging it to the 100%, and if I am utilizing it, I am able to utilizing it's only up to 90% or 80%. So total charged energy minus total discharge energy divided by the total energy. Then we will get the round trip efficiency. So out of our battery, only 80 to 90% is usable. So remaining will go as a waste in heat and conversion process. So energy density is around 0.1 to 0.5 kilowatt per kg. Self discharge rate in battery, lithium ion battery is 2 to 10% per month. Typical duration is minutes, hours up to 8 to 12 hours. Ideal for daily cycling, short duration balancing, rapid response to the demand signal, milliseconds it will respond. Limited seasonal storage capability due to self-discharge, smaller footprint for equivalent short duration capacity. Whereas the hydrogen storage is the efficiency is only 18 to 46%. See the major difference. The battery storage where it gives 80 to 90% energy storage and hydrogen gives only 18 to 46. Because electricity, what 100% we are supplying to the electrolysis, this process while converting it will be only 65 to 70% efficient. So this electrolysis will go into the water splitting process. There it will reduce to 60 to 50%. Then again that hydrogen produced is supplied to the fuel cell where 40 to 60% efficiency will be there. Again, this will produce energy as an output to 18 to 46% only. So the energy density is 33 kilowatt hour per kg of hydrogen. Then self-discharge rate is negligible with proper storage. If you are able to store the hydrogen properly, then there won't be any self-discharge. The duration will be days, months, and seasons. It can be stored for longer duration. Can store vast quantity, any quantity we can store. Versatile end use application. We can use for power, industry, transport, any application. So seasonal storage potential. So seasonal, how we can store the hydrogen. The storage capacity comparison of hydrogen is around 10x pumped hydro. So the 100x more energy we can store when compared to the hydropower plants. So high renewable energy grid requirement, 100 plus terawatt hour seasonal storage. Then storage technology potentials are hydrogen underground can be stored 500 to 1000 terawatt hour. Pumped hydrogen is 8 to 10 terawatt hour. Battery system 1 to 2 terawatt hour. renewable integration and sector coupling. The renewable energy can be integrated with hydrogen production. Like energy is produced from conversion factor 30 to 50%, then solar 25 to 35%, then hybrid system from both around conversion factor 74%, then hybridization benefit it will get add up 25 to 45%, then it is supplied to the electrolyzer hydrogen, and this hydrogen production produced hydrogen can be used in industry like steel, ammonia manufacturing and other chemical industry. Then power it can be used for power generation like fuel cell, turbines and other things. And this can also be used for transport application. So this is the combination. This the energy, the major heat source required is from the renewable, integrated renewable. Hydrogen turbine operation. So project case studies. So globally, how projects are planned, how much it is, how much investment is happening. So Dr. Jatar, whether I am running out of time or is it okay?
Sir, you can move fast. That will be better.
Okay, okay.
Yeah.
Project case studies. These are the project overviews of different projects. Japan and South Korea are developing around 20% co-firing, mixed firing by 2027, then plan for 100% ammonia by 2050. This is the quantity they planned, investment, and the long-term application. Then European Union project overview, then United States overview. We can just go through. Then storage challenges, compression, liquefaction, and materials. So different storage methods, how we can store, what parameters it will affect, advantages, disadvantages. Like compressed hydrogen, the technology is almost sufficiently mature. The key parameters is around 350 to 700 bar pressure we have to maintain to store compressed hydrogen at ambient temperature. Type 3 and type 4 composite tanks need to be developed. So high pressure sustaining tanks need to be developed. So energy penalty or energy loss is 4 to 15% of hydrogen at high heat value at 700 bar. So volumetric density is 350 at 350 bar 23 kg per meter cube, whereas 700 bar it is 40 kg per meter cube. So advantages are simple, mature technology, fast charging, discharging, no conversion losses, limited volumetric density, high cost composite material. So LCOS implication is 0.3 to 0.7 dollar per kg hydrogen at this bar 300 to 700 bar. Lowest LCOS for OS for short term storage. Liquid hydrogen storage is commercially viable, which is cryogenic in nature. Around 20 Kelvin, we need to store hydrogen nearly ambient pressure. Double walled vacuum vessels are required. So the losses is 25 to 35%. The amount of hydrogen storage is nearly 71 kg per meter cube, 70% of liquid density. So it has a high volumetric density established for industrial hydrogen. This high energy for liquefaction, continuous boil off losses, complex insulation is needed. Then LOHC emerging technology. This needs liquid at ambient condition. It will be liquid at ambient condition. Chemical bonding. Then the losses are 30 to 40%. The storage capacity, the volumetric density is 57 kg of hydrogen per meter cube. So ambient temperature pressure uses existing liquid infrastructure, no boiling losses, complex catalytic systems are required. So material based, it is still under R&D stage. So metal hydrates like MOFs, metal organic frameworks temperature and pressure varies by material. So hydrogen is stored in a within metals in the form of metal hydrates or organic solvents. So variable like metal hydrates 10 to 30% losses will be there. Metal hydrates 100 to 150 kg per meter cube can be stored, or 15 to 60 kg in metal organic framework. So potentially higher density, low pressure operation is required. Safe storage, material cost and availability are most important parameter. Heat management challenge are challenges. Limited cycling stability, because within same metal we cannot convert that into metal oxide and again convert pure metal again metal oxide. It will erode the original metal. So transportation infrastructure and cost. So I will just try to move little bit faster. So safety standard and regulations. So the safety standards like ISO, TS certification. For safety standard ISO 15916, operational standard ISO 1988001, technical standard, then IEC, International European Electrochemical Standard. These are the standards which focuses on this parameter. Key requirements are given and impacting the which industry it is related. So material and hydrogen embrittlement. So hydrogen embrittlement risks. What are the risks involved in this? So mechanism and vulnerability. Hydrogen atoms diffuses into metal lattice, causing reduced ductility, material strength, delayed cracking under sustained load, accelerated fatigue, crack growth. So these are the mechanism how hydrogen is stored in the metal, and these are what are the challenges, then how to mitigate those challenges. So mitigation strategy is aluminum alloy excellent resistance. uh, Aluminum alloys provides excellent resistance. Then copper alloys are very good at corrosion resistant, and this can be used for multiple cycle for storage. Nickel alloys are also good for high temperature applications. Then preferred stainless steel grades are 316L. And these are the summary of different metal alloy form hydrogen storage. So water requirement and sourcing, how much water is required to produce per kg of hydrogen. Theoretically, minimum of around 8 kg of water is required to produce 8 liter of water is required to produce 1 kg of hydrogen. EM electrolysis is around 16 kg liter of water is required. Alkaline, it is slightly higher. SOEC, then with desalination, it is highest. So efficiency losses across the value chain. The electrolysis is around 65 to 70%. Compression 4 to 15%. Storage 2 to 5%. Transportation 3 to 10%. Reconversion 35 to 60%. And end use applications specific, it is around 18 to 46%. It will be around 18% available at the end use application. So emerging technologies are next generation electrolyzer technology like anion exchange membrane electrolysis, advanced the catalytic system, pressurized the stack design, and this advanced system integration also most growing field now. The high temperature surface integration, advanced hydrogen carriers, digital twin, and AI optimization. These are the different technologies which are emerging. So cost roadmap 2030, 2040, and 2050, how the green hydrogen costs are expected to decline. The efficiency improvement trajectory. So PEM electrolyzer efficiency 25% can be improved by 2050 due to the upgradation of the technology. SiC with heat integration can be increased 40% by saving the waste heat energy. The system level optimization key efficiency drivers are PEM stack advances, then heat recovery and integration, high pressure operations. So breakthrough R&D and AI integration, artificial intelligence and advanced analytic applications are used to optimize the process. So increase in hydrogen technology patents 2022 are 47%. Global hydrogen R&D investment increased to 15.8 billion. So AI powered operational optimization is electrolyzers are controlled optimization algorithm increase in efficiency by 8 to 12% through real time parameter adjustment. So artificial intelligence is used to regulate the electrolyzer to predict and predict the maintenance system or to predict the failure of the system on before time to avoid any mishappening and remind the preventive maintenance at a regular interval of time. So digital twin systems are there, virtual commissioning options are there, the new emerging technology. The material innovation and system integrations are advancement is happening, like advanced material discoveries, different new materials are discovered to store hydrogen, which can deliver hydrogen at higher efficiency and higher storability capacity. So key takeaway from this presentation is key hydrogen progress dashboard. Clean hydrogen share is less than 1% now. Electrolysis capacity is 1.75 gigawatt hour. Announced investments are huge, around $680 billion. Project at FID is 4.6 million ton per annum. Cost gaps versus gray hydrogen is 1 to $3 per kg. Still, this gap is there. We are unable to meet. If we are able to break this cost gap, then it will be a reliable source. Funding gap of 335 billion is today's lacking. The critical priorities are demand creation via carbon contract for differences and mandates. So governments may what we can say government may implement or put more taxes on carbon footprint or more carbon generation or CO2 generation. If any industry is producing more carbon dioxide, they can put more tax on that one, carbon tax we can say. So by that way, the industries will move towards the greener pathway. So infrastructure build out, then standard harmonization standards need to be implemented. Water management should be improved. So today's status as of 2024, 97 million tons of hydrogen, that is still less than 1% green hydrogen is produced. So by 2030, it is expected to 12 to 18 million ton per annum. That is around 30% every year. So path forward is demand creation, regulatory clarity. So government should create a proper guidelines, policies to incentivize to promote green hydrogen production and utilization. Infrastructure should be developed and regional focus should be considered. So strategic vision and call to action 2025 to 2030 unlock offtake, implement carbon contracts for differences, then establish sectoral quotas and mandates, compulsion of generating green hydrogen, then standardize and certification framework, scale electrolyzer manufacturing. Then by 2030 to 2040, infrastructure scaling should happen, develop hydrogen industrial hubs, repurpose natural gas pipeline 10,000 plus kilometer for hydrogen transfer, establish import-export terminal, deploy hydrogen storage at terawatt-hour scale. And 2040 to 50, global trade, The mature global hydrogen derivatives market should open and different countries should sell and buy the hydrogen. So integrate shipping routes and port facility, achieve cost priority with fossil fuel, enable decarbonization across sectors. So policymakers, they have to clear long-term regulatory framework, implement demand-side measurement alongside supply incentive, streamline permitting the renewable energy and hydrogen infrastructure. For industry, what it can do from offtake consortium to aggregate demands and reduce risk. Scale manufacturing can be increased, standardized, integrated systems can be developed. For finances, they, the new investments can be done on the hydrogen production. Establish the hydrogen specific investment funds can be created. Green bonds can be released. Build expertise in technical due to diligence for hydrogen technology. So success metrics and checkpoints are our target should be bringing green hydrogen cost $2 per kg by 2030. This should be our target. And 300 gigawatt hour of electrolyzer capacity by 2030. 40 plus million ton of clean hydrogen production, then 10% industry emission reduction, and 150 million ton of clean hydrogen demand by 2050. Thank you for your patience and listening for this almost, I think, 1.5 hour.
Yes, sir. It was a really great and marathon session. Okay. We have some queries in the chat box.
Definitely.
Yeah.
Please.
Uh,
Mm,
how
Eric,
effective hydrogen storage in metal hydride in hydrogen storage, and how soon can we see the use in commercially? Its use in commercially.
Yeah, as I shown, the technology is underway. The metal storage are at a still under very advanced stage, very beginning stage. So because of its conversion efficiency, this technology still needs improvement. So not nearly, I can say around next at least 5 years, we are not able to get a metal hydrate storage because of its efficiency.
Okay, okay, sir. Any question from participant?
Hello.
Yeah.
Yes, sir.
Yes, sir. Am I audible?
Yeah, yeah.
Yes, yes.
Sir, there is one question. My name is Ajay Visabe. Instead of means promoting the green hydrogen reforms, the government is promoting the green hydrogen reforms, that is to higher extent of production. Why can't we focus on the gray hydrogen, since it will be very easy to retrofit the existing IC engines and use the gray hydrogen in it as a fuel. Also, when we look at the cost initiative, the gray hydrogen is costing around 120 to 160 rupees per kg for a common man. Then why a common man would shift to the green hydrogen, which is costing 500 to 600 rupees per kg? So why can't the efforts be made in focusing the use of gray hydrogen in by retrofitting the IC engine? And secondly, when we talk about reducing the cost by 2030, it has been observed that government has imposed the tariffs on the hybrid vehicles more. On the hydrogen vehicles more. Instead, it has lowered the tariffs on the electric vehicles, that is around 10 to 15%, and around 40% to the hydrogen vehicles. So this is a very contradictory situation. What's your view on it?
Yeah, yeah. So your first part of your question is why can't we promote gray hydrogen? So what is the need of promoting gray hydrogen? We can directly use the fossil fuels because both are contributing same carbon footprint. So that is the main reason the technology moving towards green hydrogen is to avoid the carbon footprint. The basic requirement is that one. So if we are talking about green hydrogen, it is only because we want to reduce carbon footprint. That is one part. So gray hydrogen is producing almost equal carbon footprint when compared to the fossil fuels. So, and the cost of fossil fuel is much lesser than the gray hydrogen. So instead of using gray hydrogen and at higher cost, it is better to use direct fossil fuels.
But we can use
That
the
is one.
blended fuel for gray hydrogen. Sorry to interrupt, but we can use the blended fuel along with the hydrogen with the different types of fuel,
Yeah,
and then we can use
yes,
it in the IC engine.
yeah. You are thinking about IC engine, but the overall perspective, your outer broader perspective, if you are thinking about the environment and the global point of view, the everyone is focusing now on carbon footprint. So how you will mitigate about that one? So you are focusing only utilizing the existing IC engine with the gray hydrogen,
Yes, sir.
right? Yeah. So if technology is upgrading, the new vehicles also upgraded vehicles will also emerge. So that will be the main intention we have to understand is moving towards green hydrogen is to reduce the carbon footprint. That is the main intention.
Hello.
Yes.
That
Thank you,
part
sir.
is over.
Thank you, sir.
Sir, I have a question.
Hello, Santosh sir.
Yes, sir.
Yeah.
Yes, sir.
Yeah. In line with that, I am having one question. Does that green hydrogen meets the zero emission?
It is expected because the energy source we are using for this electrolysis is expected to be received from the renewable sources.
Okay. And another question that if it is
Yeah,
hydrogen,
I have a question, sir.
Yes, yes, one by
Hello.
one, please.
Hello.
Yes, one by one, please.
yes. Shall I ask?
Yes, you go on.
Okay. So how we can calculate the range with the hydrogen cell vehicle or hydrogen fuel cell vehicle? If it is applicable for that any kind of vehicle, a range can be calculated. So how we are going to calculate the range?
That is a more specific question. So, like, how can I would like to explain is depending on the vehicle, like we are using, for example, if you are using petrol vehicle as a two-wheeler, it will give different mileage. If you are using petrol car, then it will give different mileage. So same way, depending on the vehicle load carrying capacity, its aerodynamic resistance, its frictional force losses, frictional losses, then gradient losses, all these design parameters will come into picture. Based on that one, the vehicle motor will be designed, and based on the vehicle motor, the power source will be designed. So, like for example, if two-wheeler, if a car can run per kg of hydrogen around 80 to 90 kilometer, then the truck can run with 1 kg of hydrogen only 30 to 40 kilometer. Same law applies here. So it is totally depend on the vehicle infrastructure. You cannot answer directly like this vehicle will go this kilometer. Yeah.
Yes,
Okay.
sir. It's a very nice clarification. I think Sushil Sate he may get his answer correctly.
Yes, sir. Yes.
Sir, I have a question on the electrical efficiency, what you have mentioned.
Yes.
One of the PEM you have mentioned the electrical efficiency is 57 kilowatt hour per kg hydrogen. Whereas in SOCE, you have mentioned the same as 70 to 80% with heat integration. So what is the common platform in which you compare the electrical efficiency?
Electrical efficiency is the amount of electricity you are supplying to convert hydrogen. So in high temperature, if we are giving uh, heat source of around 700 to 850 degrees centigrade, obviously it will consume more thermal energy rather than consuming the electrical energy. So the electrical efficiency will be higher in that application when compared to the PEM. Yes, next question, please.
What are the current research approaches in green hydrogen?
Yes, you are
Sorry,
not audible.
pardon?
Yes.
Sir, what are the research approaches in green hydrogen?
What are the?
You are not audible clearly, Dr. Trijo.
Please repeat. We are not.
Please
You are
repeat
not
your
audible.
question.
We are unable to capture your query.
Dr. Trijo, are you there?
Yeah, I'm here. Am I
Yeah.
audible?
Yeah.
What are the current research approaches in green hydrogen?
What are the current research
Opportunities.
opportunities? Okay. So when if we are talking about India, there are very little opportunities available because it is still in a beginning stage. So only specific like prestigious institutes like some IITs and IIC is working on the hydrogen fuel cell. So to be more specific, the opportunities are very limited.
Okay, sir. Thank you very much for your informative and nice session. I hope that all the questions are clear to everyone.
Okay, thank you
Okay,
very
sir.
much.
Yes,
Okay,
thanks a
thank
lot.
you for
Yeah.
thanks for giving me this platform to share the brief perspective of this hydrogen fuel cell. I thank everyone for your great patience. Thank you.
Thank you. Thanks a lot, sir.